results are the same for a wide range of viscous units between input and output from 1 to 10. And so I'm going to be focusing on the results for 5 viscous units. And the key of this architecture, this is a U-net. In a U-net, I basically apply convolutions. Then at this point, I apply basically a pooling layer. So I just reduce the resolution. I apply more convolutions. Again, another pooling layer to reduce the resolution. And then at this point, I'm doing a transpose convolution. So I increase the resolution. And over here, I will increase the resolution again all the way to the output. Okay, so I have convolutions. And then I have these green arrows here, which are the key of these unit architectures. These are basically skip connections which determine residual blocks. And these ones are connecting feature maps from early in the network, which are typically more abstract. These are simpler features that have been identified in the data, with feature maps close to the output, which are much more refined. Remember that convolutional networks work by hierarchically combining more and more detailed features. Therefore, if I combine feature maps from quite early in the network with feature maps which are quite much more evolved, basically, then I can improve my predictions, right? And the reason to call this a U-net is because of this U-shape. So the highest resolution is at the top, the lowest resolution is at the bottom, basically. Okay. So this is my architecture for making my predictions. This is my surrogate model. We get less than 1% error in our predictions, so we get very, very good accuracy. And this is how I would really calculate my SHAP values, my importance score. So I would have, again, U, B, and W fluctuations in the present. I would run this input through my U-net to calculate U, B, and W fluctuations 5 viscous units into the future. Okay. And then I would calculate my error, which would be less than 1%. And then I start to remove features from my input. I start to remove these Reynolds stresses, extractors. I repeat my prediction. And if after removing that structure, the error has increased a lot, that means that will be important. So they will have a high importance score or SHAP value. If the error didn't change very much, it will have a low SHAP score or SHAP value, basically. Okay. Now, with this information, let me tell you a bit more how we actually calculate that importance score. The key is this function G. This is a linear model for the error between the neural network and the ground truth. So we're going to assume that that error can be expressed as a linear superposition of all the structures in the flow. So Q1, Q2, Qn with the binary variables, which take the value of 1 if the structure is present, or 0 if the structure is absent. And this phi1, phi2, phi-n, these are weighting factors which determine how much that structure contributes to the error, basically. So this linear superposition allows me to define the error between the neural network and the ground truth. And what I want to do is minimize this least square regression problem, where f hat is the true error between the neural network and the ground truth. I want to make this difference as small as possible, which will basically allow me to find the values of these SHAP scores, of these weighting factors. This pi x here is a kernel, which is based on game theory, selecting those coalitions. I'll tell you more about it in just a second. But before proceeding with the results, I want to revise 2 main assumptions that we have with this method. The first one is that the model G is linear. The model explaining the error in this high-dimensional system is a linear model, right? Of course, this is a turbulent channel flow. This is, chaotic, non-dimensional, complex. So can a linear model reproduce that complexity? And the truth is that we have so many structures. We have about 100 structures per flow field. That the difference between the true error and the linear model of the error is on the order of 10 to the minus 7. It's many orders of magnitude smaller than our fluctuations. So this means that even if linearity in this case is an approximation, I have so many structures that considering only their linear interactions to contribute to the error is sufficient to have a pretty good description of my performance of the model. Second, when I'm removing structures one by one, I'm really not accounting for the interscale interactions that happen in a quite complex chaotic flow. The reality is that I am not really doing it one by one. If you remember from the previous slide, this kernel over here, that's creating coalitions. And a coalition is a group of structures where the role of my structure of interest is analyzed. So each structure is assessed in terms of importance in many contexts, sometimes together with structures close to the wall, sometimes together with structures farther away from the wall, in such a way that the role of that particular structure can be assessed in many contexts, reproducing in a way the complex interscale mechanisms present in turbulent flows. So that's actually a way to really account for that chaotic behavior that we have in turbulence. And we have really assessed the performance of our method versus the number of coalitions, the number of structures per coalition, and we have really converged our results. So we're pretty confident that what we analyze is a very good representation of these error levels from the different structures. Okay? So let's look at the results. Remember that we are looking at Q events, so Reynolds stress structures in my input. I'm showing you here the SHAP value, so the importance as a function of the volume, and there is a pretty good correlation. So larger structures are more important, which is expected. That's good. They are split into 4 different quadrants. The blue color is the ejections. So the ejections are in principle the most important at this low Reynolds number. But what happens when I scale the importance by the volume of the structures? So in the vertical axis, I have importance divided by volume. In the horizontal axis, I have the volume. Well, actually, things change. The largest structures, which are found in this blue balloon over here, they are not the most important anymore. The most important are in this red balloon, the most important per unit volume, and those are medium-sized ejections. So that's a very important thing to keep in mind. Ejections are basically regions of fluid that are being pushed away from the wall. Okay? They are going up and backwards. Now, if I analyze the Reynolds stress of these structures, because remember, these are 3-dimensional regions containing high Reynolds stress, then I can see in the right panel, again, a pretty good correlation between the importance and the Reynolds stress. So the structures with the highest Reynolds stress are the most important. But when I scale things with the volume, things change again. In the vertical axis, I'm showing you the importance per unit volume, and in the horizontal axis, I'm showing you the Reynolds shear stress per unit volume. So now the correlation is gone. Now I have 3 different regions. In region A, I have a pretty big spread. So for the same volume, we have a broad range of values of importance. In region B, I have the structures with the highest Reynolds shear stress. And in region C, I have the structures with the highest importance. And now is when we start to see interesting things, because this tells me that even if I'm only analyzing structures based on the Reynolds shear stress, the most important ones are not the ones with the highest Reynolds shear stress. There is something else happening in the flow. And that really tells me also that the classical knowledge or the classical perspectives on turbulence might not be always true if we don't use an objective measure of importance, an objective way to analyze our data. Okay? So this is one important conclusion from today. The next conclusion has to do with the data that we're using. I mentioned that the advantage of our method is that it doesn't need to be applied only to numerical data. It can be applied also to experimental data. So then we talked to Ivan Marusik's group, and we used their basically this towing tank experiment that you can see over here, where they have this very big plate that is set into motion. And because the plate is moving, the boundary layer is growing in time, as you can see here downwards. So this is a temporally evolving turbulent boundary layer. And the reason to use experimental data is twofold, actually. The first one is experiments are usually at higher Reynolds numbers. So if I analyze the important structures in a low Reynolds number DNS, very nicely resolved, those important structures might not be the same as those in a very high Reynolds number experiment. Maybe yes, maybe not. And second, even if I could do a DNS at the very high Reynolds number of an experiment, in the DNS I have 3-dimensional, nicely resolved data. In the experiment, I can measure, if I'm lucky, maybe a 2D plane with PIV, which is noisy, with low resolution. So the question is not what are the most important structures in the flow. The question is, from whatever I can measure, which is not the whole flow in the highest level of detail, from whatever I can measure, what are the most important structures? That's my question. And the data that we got from Ivan's group is very similar to the experiment, to the numerical one, very high time resolution, just that is 2D, right? So we have a 2D plane measured with PIV, and the Reynolds number is 1 order of magnitude higher. So this is 1,300 friction Reynolds number. So let's analyze the results and compare them with the ones from the simulation. On the left, I'm showing you the importance as a function of the surface of the structures, so not the volume anymore, but the surface. The pretty good correlation between size and importance is also found in the experimental data. The ejections are still the most important, but there is a relative increase of importance of the sweeps, this yellow region over here. The sweeps are flow that is going towards the wall. And this is expected as the Reynolds number increases. Okay. Now, on the right panel, I'm showing you the importance per unit surface as a function of the surface. Once again, in this blue region over here, I see the structures which are the largest, and they are not the most important. The most important, like in the case of the simulation, are in this red balloon over here, which contains the medium-sized ejections. Now let's look at the Reynolds stresses. On the left, I can still see a good correlation between the importance and the Reynolds shear stress, right? I mean, the UV. So the structures with the highest Reynolds shear stress are more important. But when I scale this importance per unit surface, which you can see that on the right panel, so in the vertical axis, I have importance per unit surface. In the horizontal axis, I have Reynolds shear stress per unit surface. What I have is exactly the same three regions as before. In region A, a very big spread of importance levels. In region B, I have the structures with the highest Reynolds shear stress. And in region C, I have the structures with the highest importance. And once again, the most important structures are not the ones with the highest Reynolds shear stress. Okay, so that confirms the numerical data. We are happy. Now, what I showed you so far was basically relying on pre-identifying the Reynolds stress structures in my input, right? And then I looked at which ones are important, which ones are not. What I really want to do is to use this explainable AI framework to identify new structures based on importance. I don't want to have to rely on Reynolds stresses, on vortices, on anything. I just want to do an analysis that will tell me which are the most important structures, regions in the flow, actually. And what we do is modify the method that I mentioned before. You can see here that in the input, I have now a mesh with the grid points from the simulation. And what I'm going to do is remove point by point the input data. So I have my UV and W fluctuations. I make my prediction. I calculate my error. And then I start to remove pixels. I remove the first pixel. I recalculate the error. If the error increases a lot, that means that that pixel was very important. If the error doesn't change so much, that means that that pixel was not very important. Okay? And we applied this method to the experimental dataset by Marusik's group. This required using a slight variation of the method, which is called gradient SHAP. The gradient SHAP gives us a value of importance for each velocity fluctuation component. So basically, I can create this norm of importance, which relies on the importance in the stringwise direction, the importance in the vertical direction, and compare this value with the underlying RMS of the importance in the flow field. So basically, I can create from the data regions of high importance. I don't need to rely on vortices, on streaks, on anything. I just look at regions of high importance. And in this snapshot in the bottom, you can see in green the structures based on importance, the SHAP structures, and in black the Q events, which are the Reynolds stress structures. And you can see that there is a bit of an overlap. There is 70% overlap. So there is some agreement, but also some disagreement between the importance-based structures and the classical Reynolds stresses. Now, we were not happy with just this comparison. We wanted to do more. And that's when we started this study, which is an extension of the previous one. This is under review in Nature Communications. What we did was to take the DNS data, channel flow, up to RE tau 550, so these are much higher Reynolds numbers, And then do the same game. So remove pixel by pixel points of the input, repeat the predictions, and then calculate the importance based on that. Okay. And what we get is pretty interesting. This is for the same snapshot. The SHAP structures are represented in the top left panel. And so in the top left, you can see what the structures purely based on importance look like. Again, this doesn't rely on any assumption about the flow. This is only based on importance. On the top right, you can see the Q events. These are the Reynolds stress structures that I showed you before. On the bottom left, we talked about streaks. These are the classical streaks from the near wall. And on the bottom right, you can see the vortices, right? The classical lambda2 or delta criterion vortices, which people typically show. These are the vortices that I have shown you in the wing visualization at the beginning, okay? So we have three classical structures and the new importance-based structures. Let's compare them. Let's look at the joint PDF, the joint probability density function of the SHAP, which you can see here in big. The vertical axis is the y plus, and the horizontal axis is the u plus, the streamwise velocity fluctuation. And I'm going to compare this probabilistic distribution of the structures with the classical ones. So at the top, these are the Reynolds stresses. In the middle, these are the streaks. And at the bottom, these are the vortices. Okay? Now remember, the most important structures are the SHAP. These are the ones that we have defined purely based on importance. The classical ones may agree more or less with ours, but ours are the ones that are really based on importance. And if we compare these panels, you can see some similarities here in blue. So this region looks a bit like this region from the Reynolds stresses, which are basically ejections. This region over here agrees a bit with the sweeps. So that's kind of interesting. At y plus 15, we have agreement in these probabilistic distributions between the low speed streaks and the high speed streaks. So that's also interesting. And at the channel center, we have agreement in this region for zero velocity fluctuation intensity between the vortex clusters and the SHAP structures, basically. Okay, so there is some agreement. What we wanted to do next was to get even more insight by looking at the coincidence, at the agreement in space between structures. So we will go for one snapshot, calculate the SHAP and all the classical structures, and then look at the one-to-one agreement between those structures. And that's what I'm showing you here at the bottom. In the vertical axis, I'm showing you the percentage of agreement between the classical structures and the SHAP. On the horizontal axis, I'm showing you y plus, so that's the wall normal distance. This orange line shows the agreement between the streaks and the SHAP. And you can see that we have pretty high agreement, about 90% at y plus 15, and that agreement quickly goes to zero. So this is expected, or this is actually reassuring. The streaks are well known to be very important in the near wall cycle, obviously, right? So the fact that they agree very well with our importance-based structures is very good. So at y plus 15, the streaks are important. Everywhere else, they're very unimportant. This blue line indicates the agreement with the Reynolds stresses. So at the wall, there is about 50% agreement with the sweeps. Far away from the wall, about maybe 60% agreement with the ejections. So there is some agreement between Reynolds stresses and these SHAP-based structures, but not so much. At the channel center, we have 15% agreement between the vortices and the SHAP, which is actually very interesting. The vortices is what everybody shows. When you create a nice visualization and you want to get some attention, you put it online, or you send something to the APS gallery full motion, people usually show the vortices, right? But what we can see here is that the vortices are very unimportant. The vortices don't really play a very important role in the flow. They are there. They are studied and represented because they are there. You can see them, but they are not so important. So what this actually tells us is that the classical studied structures only paint a partial picture of wall-bounded turbulence. So depending on where you are, the classical structures may have more or less importance, but none of them reproduces the whole picture that is painted by the SHAP structures, by our importance-based metrics. Okay? So that's the first message that I want you to get from this presentation. We can use our SHAP framework to identify the most important structures in the flow, and hopefully we can use that information to remove it. So if we can remove those important regions from the flow using deep reinforcement learning, we might be able to get very highly performing control strategies. Okay, for example, tackling drag reduction. So, what is deep reinforcement learning? I'm going to give a very brief introduction. We have many articles where we work with this, and a lot of this work was started early by my former student, Luca Guastoni, who is now a postdoc in Munich, in this study over here. And we have also a review paper written by Vignon and others in physics of fluids, where we have a very comprehensive recollection of the reinforcement learning applications to flow control. So if you want to learn more, feel free to check these references. In a nutshell, what we have is an agent, and our agent is typically a neural network, which is interacting with an environment. And in our case, the environment will be a simulation of the flow or an experiment of the flow. I'm going to be showing this for a numerical implementation. The agent is interacting with the environment through actions, and those actions are actually the control. So in our case, we want to put jets on the wall and do blowing or suction to control the flow, to diminish the drag. Those actions are going to change the state of the flow, and the state is our observation of the flow. And they're going to provide us a reward. And the reward is a measure of the quality of those actions under a certain norm. For example, drag reduction. I do actions, I try to do different things. The drag reduction will tell me how good those actions were, so that will be my reward, basically. And the agent will basically interact iteratively with the environment in order to create a policy pie, which, given the state of the flow, is going to select the actions that will maximize the reward. Okay, that's my idea. I want to create a mapping state action such that I can maximize my reward. So I'm going to be using a Turbulent open channel as my benchmark. Okay, just to try different control strategies. This is at a Reynolds number 180. It's a friction Reynolds number of 180. And I'm going to consider both a minimal channel and a full channel, just to be able to train more efficiently. Our benchmark method for control is going to be the well-known opposition control. So in opposition control, you can see the definition here. What you do, if this is the wall, is that you will sense the flow above the wall, typically at y plus 15. You will sense the vertical fluctuations, and you're going to do the opposite at the wall. If you have a positive vertical fluctuation, you will do suction. If you have a negative fluctuation, you will do blowing, to try to, in a way, oppose those fluctuations in the near wall region. Okay, and of course, this is an empirical model. This is a bit simplistic. It still works pretty well. What we want to do is assess whether reinforcement learning will allow us to discover something more complex, right? A bit of a more interesting and sophisticated relationship between the state and the action that I take. And to do this, we use something called multi-agent reinforcement learning. In multi-agent reinforcement learning, what we want to do is exploit the invariance in the flow. What does this mean? If we consider a turbulent channel, we have periodicity in the stringwise and spanwise directions, which means that the flow, even if it's instantaneously different in different points in space, statistically is basically having the same information. You will converge to the same profile. So what we do is that we can divide my space into these pseudo environments that you can see here, these blue regions here. These pseudo environments contain copies of the same agent. Okay, so the same agent is copied many times. I received a state observation of the flow, which contains the U and V fluctuations at y plus 15. And then the agent needs to decide the actions, which are the blowing or suction, to be able to maximize the reward. And then what I do is the following. I can train this agent in many parallel instances, because all these pseudo environments are having the same statistical information, but they're experiencing instantaneously different flow behaviors. So I can speed up massively the training of my model. And also the multi-agent reinforcement learning allows the agents to cooperate, because the reward is global. So I want to minimize the drag, in this case, the skin friction coefficient over the whole wall. So the different pseudo environments that see different parts of that overall goal, they start to cooperate to reach the highest possible reward. Okay. And this was work led also by Luca Bastoni. We discussed this in detail with Steve Branton and Beverly McKeown in Nature Reviews Physics. So we had also pretty good discussion on the implementation of this for experiments. Okay, the key is if you want to apply reinforcement learning for turbulence, where the dimensionality gets pretty high, you need to do multi-agent reinforcement learning. Okay, that's our experience. These are the results. In blue, I'm showing you the results from reinforcement learning. We get 30% drag reduction. In orange, from opposition control, only 20% drag reduction. So we are 50% better than opposition control by coming up with a much more sophisticated control strategy. In fact, if we look at the quadrant analysis, this is basically the joint PDF of the stringwise and the wall normal fluctuations at y plus 15. In the top panel, what you see is a predominance of the top left and bottom right panels, right? Which interestingly, the top left corresponds to the ejections and the bottom right corresponds to the sweeps. So this basically confirms what we saw using SHAP in the first part of our presentation. In the uncontrolled flow, ejections and sweeps are dominant. If I do opposition control, you look at the second panel, and even if the range of the fluctuations has shrunk, the predominance is still on the ejections and the sweeps, right? So you haven't really fundamentally changed the flow. You have to just reduce a bit the fluctuation range. In the last panel, by looking at this PDF, what you see is a pretty even distribution of the fluctuations across the 4 quadrants, which means that we have significantly affected the flow with reinforcement learning, and we have a pretty different control strategy. In fact, what this control is doing is completely stabilize the streaks. I mean, the streaks are still there, the flow is still turbulent, but the meandering is pretty much gone through the actuation that we obtain from reinforcement learning. Okay, so this is good, this is promising. Now, can we combine the first and second parts of the presentation? Instead of using as a reward minimization of the drag, can I identify the most important structures in the flow, which I did with SHAP before, and in my reward, aim at minimizing the most important structures on the flow? It will be actually pretty neat, right? So I'm going to be using this color code for the next slides. In blue, I'm going to be using opposition control. In orange, this is reinforcement learning for reducing the shear. And you can see the different rewards here at the bottom. In orange, the reward is just to reduce the shear stress, basically what I just showed you. In green, the reward is going to be the minimization of the Q events, so basically the Reynolds stresses. And in red, the minimization of the streaks. In purple, I'm going to be showing you the results that we obtain when we minimize the SHAP structures. So the importance-based structures in the flow. Okay? And I'm going to show you what drag reduction we get in each of these scenarios. The top panel is showing the drag reduction as a function of time, and the different lines correspond to the different cases. In orange, you can see the drag reduction from the reinforcement learning, where the reward is to just minimize the drag, and this is 31% drag reduction, what I showed you before. The blue line is the opposition control, which is about 20% drag reduction, again, what I showed you just a few minutes ago. And what I can show you now is what happens when I look at the classical structures. In green, this is the minimization of the Reynolds stresses, so only 27% drag reduction. Minimization of streaks is even worse, only 21%. In purple, this purple line over here shows the drag reduction when I minimize the importance-based structures. So I first use SHAP, I identify what's the most important in the flow, and I use reinforcement learning to find ways to minimize the most important structures in the flow. That gives me the highest drag reduction, as you can see, 5% better than the orange line, than naively reducing the drag. Not only that, I get a much more stable control. You can see that the oscillations are much narrower. So not only I can reduce the drag more, but I can get a much more stable control. And what is interesting, if you look at the bottom panels, here I'm showing you the reduction of Reynolds stresses, and here I'm showing you the reduction of streaks. In fact, the policies aiming at reducing the Q events are the most successful in reducing Reynolds stresses and reducing streaks. but that does not translate into more drag reduction. This really shows that the SHAP structures are the most important in the flow. When I minimize any of the classical structures, the drag reduction is much lower. When I minimize the SHAP, the importance-based features, then my drag reduction gets much, much higher. There is yet another advantage of using the SHAP for flow control, and is that it has a much lower power consumption. If I define my net energy savings, which include the skin friction reduction and the power input of the actuators, in orange you can see the drag reduction from reinforcement learning to minimize the drag, and in purple the drag reduction when the reinforcement learning is used to minimize the SHAP. You can see that the power input is about half. So the net energy savings are 5.4% better than the naive drag reduction. So to wrap up this part of the presentation, I still want to show you one more example. But to kind of summarize this part of the presentation, we first identify the most important structures in the flow, and then we use reinforcement learning to find smart ways to diminish, to reduce those important structures in the flow. That gives me the highest drag reduction at a reduced power consumption. Okay. Now, the next thing that I wanted to show you is how to apply reinforcement learning for flow control in wings. This is a turbulent wing. This is almost DNS resolution simulations that I performed now 7 years ago, Reynolds number of 200,000. So this is a reasonably high Reynolds number. To apply reinforcement learning here, in particular to apply multi-agent reinforcement learning, gives me many headaches. The first one is that I only have one periodic direction, so I can only exploit invariances in one line. The second one is the fact that when I'm trying to train on this region at the middle of the wing, I still need to simulate the small scales close to the leading edge, which limits significantly the time step of my simulation, making things more expensive. And finally, a wing is very expensive. I mean, you need to really simulate a lot of grid points to be able to reconstruct this geometrical complexity here. However, we can try to do something a bit different. We can look at a region of the wing, look at this box over here, expand it, and use a turbulent channel. In a turbulent channel flow, I can have a very large domain with many pseudo environments, so many periodic directions, therefore accelerating my training by a factor of 20. I don't need to simulate the small scales close to the leading edge because I need to simulate the scales that I'm interested in. Therefore, I can increase the time step of the simulation by a factor of 3. And the channel is 176 times cheaper in terms of grid points than a turbulent wing. So by using a turbulent channel to train my reinforcement learning method and then deploying that reinforcement learning method in my wing, I can be 60 times faster and over 10,000 times cheaper. This is really a very good way to train our models to deploy them later on in our simulations. And this is work done together with my two PhD students, Juning Wang and Paul Suarez. When I apply this methodology in the wing, you can see that the drag reduction from the reinforcement learning, which is the blue line here, is much higher than that from opposition control. So we get around 25% drag reduction with the reinforcement learning, around 20 only with opposition control. So we are 20% better than opposition control when deploying reinforcement learning to control the skin friction in turbulent wings. Okay, so and this is, of course, ongoing work. This is something very promising that we think is really help us a lot to scale up the application of reinforcement learning in complex industrial settings. Some more examples in this work by Bernard Font and collaborators. We use reinforcement learning to control separation, and this is published in Nature Communications. We got much better performance than with classical control. Here you can see the application to cylinders in 3D at progressively higher Reynolds numbers. This is work by Paul Suarez, just published in Communications in Engineering. And at the bottom, you can see our application to relaminar convection in 3D. This is work by Joel Basanth, where you can see how the convection cells really realign in very different patterns when we want to minimize the Nusselt number. So this is really giving us a lot of interesting performance and applications in the context of heat transfer applications as well. And a summary of what I talked to you about today, we use SHAP, explainable AI, to be able to identify new coherent structures purely based on importance. Reinforcement learning gives us much better potential for reducing drag than classical control methods, about 50% better than classical methods, also in turbulent wings. And finally, the combination of the explainable AI to identify the most important features in the flow and reinforcement learning to minimize those features in the flow gives us the highest drag reduction and a lot of potential for a very wide range of applications. You have a lot of material, all the codes and all the data in my repository of my research group. So you can use this QR code over here to access all the information. I have a lot of lectures and videos in YouTube, so you can also access my YouTube channel, and you can find me in social media or by email. So there's many ways to reach me if you want to collaborate or discuss. For now, this is all I have, and I'm very happy to take your questions and discuss a bit more.
Thank you, Ricardo, for this fascinating talk. So, any questions from the audience? I can start with one, which is very specific. Then I have a more general one that I can ask at the end of the talk. So you mentioned on the deep reinforcement learning for controlling the flow.
Yeah.
You use this splitting of the domain and having one neural network, so this multi-agent. I found this was a very good idea because in addition to exploiting the translation invariance, right, of the problem, you also reduced a lot the action space for the agent, right? Because now the agent only needs to control the actuators that are there in that small grid, right?
Exactly.
So that's great. But then you mentioned that they can also learn to cooperate. And so my intuition is that in order for this to happen, the neural network needs to have some awareness of which grid it is controlling. So do you pass as an input, like the location of that current grid for the neural network? Or?
Yeah, that's a good question. So this is an MLP, a multi-layer perceptron. So basically, we know, basically based on the location of the data in our input layer where everything is, but we are not explicitly exploiting spatial distributions. This is not any convolutional architecture, which is one of the extensions that we are looking at, but we're not doing that yet. This is just purely based on the location of the input within that MLP.
Okay, so because they get the, let's say, the X, Y coordinates, they implicitly are aware of they are located.
Exactly.
Okay, excellent. Okay, so I'm moving on to a question from the audience, and then I can ask mine at the end. So, Guilherme.
Right, you cannot see me. Hello, Ricardo. This is Guilherme Vaz. I'm from Portugal.
Hi.
So I have a question regarding, this very nice research you're doing on turbulence modeling. I work more in the industrial applications of CFD. So I was wondering if you are trying, or you've already done, connecting some of the things with traditional turbulence modeling that is used for industrial purpose, or you are putting this in some code that people can use it. My question is more towards the application, the real applications, industrial applications, if you are connecting with them somehow.
Yeah,
thank you.
That's an excellent question. I work a lot with industry. We have many collaborators and many industrial projects also, both in Europe and in the US. So there's different, specifically about modeling. We have done some runs modeling. I think the biggest potential is with reinforcement learning for LES modeling. And we have now several projects on being able to develop new wall models with reinforcement learning. The advantage being, if one thinks about it, right? Because there's a lot of work on supervised learning. So you have your core simulation, you have your DNS, and then you want to really create a closure term. And with supervised learning, you can close the gap, basically. Well, that doesn't really work so well when you want to do a posteriori tests. But with reinforcement learning, you have a much more dynamic way to create a closure. So that's something that we have shown that it works really well for wall models. So your reward in this case is not match the DNS, but match some correct physical properties of the flow, like maybe match the correct spectrum of the flow, or match the log law, right? Something known about the flow. So that works really well in the context of modeling. And we're also working in parallel with self-supervised learning and generative AI for closure purposes as well. And that's also having a lot of potential. So yeah, so those are two areas where we believe there's quite some novelty and application. And finally, in the context of reduced order models and surrogates, I didn't talk about it today, but we have also several studies in Nature Communications on using autoencoders to create surrogate models, which can be very helpful for optimization. So that's also something that we are doing. So instead of doing optimization in the full dimensional DNS, we just create a very compact, very efficient autoencoder-based surrogate and do the optimization there. So I would say that for modeling, there are many possibilities, and also for reduced order modeling for optimization, there are many possibilities as well. And I'm happy to discuss more afterwards. If you send me an email, we can have a chat.
Yeah, for sure, because I'm more close to the industry and I work a lot on scale resolve simulations, more a traditional one. I was also continuing, we have time for another question, is like, what is the role of numerical errors in all this approach? I mean, you are here considering the flow as it is real, and you spoke about the ground truths. Well, that's for sure, even if you do a DNS, there's numerical errors, there's never the ground truth. So how can you somehow consider the uncertainties of the numerical errors you have for the so-called ground truths?
Yeah, no, that's a good question too. I mean, of course, when we do very highly resolved DNS, I mean, that we can consider that to be a very close resemblance of the ground truth. But we have also incorporated UQ methods. So we have some assessment of the uncertainty in our predictions, particularly when we start to do the game theory part for the explainability. You can look at sensitivities and which parts are really contributing more to the error and to the uncertainty and so on. So I would say that for the numerical part, having DNS and some UQ on it, we are covering that, but we're also working in parallel to implement this experimentally. So we have now some work where we are doing the reinforcement learning for control of wakes in a wind tunnel experiment. And we are trying to expand and scale up the applications to do it in larger models also in wind tunnels.
Thank you.
More questions from the audience? Okay, so I'll ask a more generic one. So your work is at the intersection of CFD and machine learning. So it seems like, what is your opinion on what is the trend in terms of having some sort of foundational model for CFD, in the sense that typically you will have to retrain your surrogate model for each particular application because you have the geometry of objects involved. And the geometry of objects can be a very high dimensional thing. And it's pretty hard for a machine learning model to be able to generalize to any different kinds of shapes of objects there. So how do you see this evolving?
Yeah, there's different parts to that question. I mean, the first one, even before looking at foundation models, if we look at reinforcement learning for closure, right, for modeling, we have observed that there is a pretty decent degree of generalization if your reward is something that is, a physical property of the flow. So not necessarily that I need to match this DNS data set, but rather the spectrum needs to be correct. So in that sense, the reinforcement learning framework is pretty adaptive to other configurations to try to fulfill those properties. So I think reinforcement learning can really help us to generalize. Now, more to the point of your question on foundation models, there is a lot of discussion on foundation models. I don't think we should be aiming at building one big foundation model to basically replace DNS, let's say, right? So to have any possible configuration, any possible problem because of the sheer amount of data and complexity, and pretty much the Navier-Stokes equations are the best way to encapsulate the information of flow data, right? So I don't think that's the goal, but I think there is quite some benefit in thinking of foundation models with certain applications in mind. So a foundation model for turbulence modeling, I think that makes sense. So it's not about covering any possible configuration, but just developing closures. And I see a lot of potential there because then that means that we would be gathering data with the characteristics and with the goal of having that particular target in mind of closure, so we can gather data efficiently for that goal. And what we have also seen is that self-supervised learning generalizes pretty well also in these scenarios with very complex, complexly varying geometries. For inverse problems, there is also quite some potential. So I would say that yes, having the strategy of creating foundation models for modeling, for example, that's a reasonable strategy.
Thank you, Ricardo. Okay, so if there are no further questions, you have one. Okay.
Hi, thank you for the presentation. I have a question on the time, the inference time of the model, because the opposition control seems so simple that it takes no time to compute. And if you're in a real application, maybe go through these steps takes time, and then it's like a lag between calculating the optimal strategy and the implementation compared to like zero compute time for the opposition. I don't know what's the...
That's an excellent question. So keep in mind that, of course, training takes time, of course, and you need to evaluate many episodes and many configurations. But once the model is trained, once you have a policy, we only need, in real time, you only need to do inference, right? We only need to have the state and then apply the action based on that. That's very fast. That's on the order of milliseconds. So what we are doing now when we implementing this experimentally, the time scales of the structures that we want to control are slower than you need to keep in mind the whole latency, right? So you need to measure something in the experiment that needs to go to the computer. You need to calculate the action and send back. All of that takes time. That whole cycle is on the order of a few milliseconds. That's faster than the time scales of the structures that we want to control. So to answer your question, this is in inference, this is very fast also.
Thank you.
Okay, so let's thank the speaker again. Thank you so much.
Thank you very much.
So now we have a coffee break, and we'll be back at 11:45. 11:45. Okay. Thank you.
Well, you can, with Synera. Synera's intuitive user interface lets you connect
Okay, I have sound now. So welcome back, everyone. It's my pleasure to introduce Jousef Murad. He's currently the founder and CEO at Apex Consulting. Jousef has a background in computational mechanics and fluid dynamics from Karlsruhe Institute of Technology in Germany. And then he worked in industry in a few different places. For example, I'll highlight two startups, SimScale and Monolith, which are working in this space of engineering. And is more widely known for his content in both Coursera, YouTube, a series of podcasts, newsletters that are followed by, I don't know how many thousands of people around the world in the CFD community. So we are really excited to have Jousef joining us in this summer school. And he will be giving some sort of overview on some trends on AI being applied in engineering, in industry. So welcome, Jousef.
Thanks a lot. Can you hear me, guys? Perfect, excellent. First of all, before I get started, big shout out to the Inductiva team for organizing all of this and for inviting me to give me this opportunity to speak. So thank you very much. I tend to speak, as you already noticed, very fast. So if I'm too fast at some point, just interrupt me and just raise your hand and ask some questions. So as Ugo already said, I'm going to talk about AI automations and agents and why are they so important, especially in the context of engineering applications in the industry. So my talk is not going to be focused on too much academic stuff, how LLMs work, etc. This is also very interesting, but I primarily want to focus on what some of the customers of ours, namely Synera, that you can see on the top left, have done using low-code language, so a visual programming language that engineers can use to kind of translate what they want to achieve in a low-code format and then apply it in the industry. Okay, first of all, about Apex, Ugo already said it, my background is mechanical engineering, so I've been working for a couple of startups, one in Munich called SimScale, then Monolith AI in London, and then somehow decided, because I don't like to sleep, to found a company, namely Apex, roughly 2 years ago, with the focus really, because my USP is I'm an engineer, I understand the marketing side of things and the sales side of things, so it obviously made sense for me to start a business. And as you can see, we work with Siemens nowadays, Altair, Navasto, which is a great startup. There was even a presentation on graph neural networks. So Navasto is one of the leading companies who work on graph neural networks. Excellent team, very smart people. Then a couple of simulation startups like Jano Simulation based in Germany, Synera, which is also based in Germany, and SimQ, who are focusing more on the medical side of things in terms of simulation. Right, and I think it's important to note what we do at Apex is not really engineering work, but I want to draw parallels between the low-code approach that we use in order to build systems and strategies and use tools for companies in order to achieve more, which ultimately is more revenue, making more money, because ultimately we can't live from love and air only, and how that applies to the engineering application when it goes to building organizational structures, agents, systems, and then deploying them. So what is important for me as a founder? So what we automate mainly, and this is not super important for the engineers here, mainly stuff in the area of sales, marketing, fulfillment, support, back office, executive management. So what does it mean? I'm very excited about the support part of it because next week I'm going to be deploying an AI voice agent. So basically what you can think of is an agent that can take calls, but also makes calls on behalf of the company. So next week we're going to launch this in beta, and I think it's going to be very interesting. There's a lot of voice agents out there already, but I think the crux of it is really deploying agents that sound like humans, and I think we're getting pretty close to it. So next week, roughly, we're going to deploy this in beta. This is going to be very exciting for some of our customers. Before we jump into the engineering application, one example of what we do in sales, for example. So this is what we call a waterfall model, just to understand what we actually do for companies. So let's say you want to look for customers, right? We always want more customers. It's great for the business, etc. What we do is, what a lot of people do is they go online and do manual search of customers, potential people that might buy from us. Could be a service, could be a product. And then what we do is, for example, there's one service listed called Apollo. What Apollo basically does is you type in your ideal customer profile, you have a vision of who could be my potential customer, and then you have kind of a drop-down menu where you can select how big is the company, where are they based, and so on and so forth. So specific parameters that you can tweak. The problem is, however, though, it's a very manual and tedious task that you have to do. So what we do is we automate this whole process. So let's say I'm looking for the CEO of Inductiva. Let's say I'm too lazy to Google, but I want to scale it, obviously. So I want to not only look for Inductiva, but all the companies in Porto and beyond. Maybe in the DACH region, maybe EMEA, whatever. So what we do is actually, we don't do this manually. We stack different tools in a low-code approach to actually do this automatically. So everything that a salesperson would do, or a marketing person would do, or even a CEO in a manual way, which is obviously not scalable and very tedious to do, we automate all of that entire process end to end. So the research, the qualification process, so you have to be very good in prompt engineering to actually see if that prospect is a good fit for your company. We would do that automatically. And the way it works is, and now this is the more interesting bit, we build this in N8N. And N8N is nothing else than kind of a visual programming language, so to speak, where you can build automation systems. So you see a couple of more complicated automating systems, for example, for lead research purposes. So instead of, let's say, I'm having a specific task, I go to Google, I Google a specific company that I'm trying to target, all of that I can digitalize or build a digital twin, quote unquote, in N8N. So it's kind of a low-code approach of how to achieve a specific task. So for example, what you can think about in the top left corner, for example, instead of researching a company and see if it's actually a fit for my company, if there could be a potential fit for my company, I do that all automatically. I give it a specific prompt. I see if it's if it matches the ICP, so ideal customer profile. I want to know the phone number. I want to know the CEO. I want to know the email addresses that that are associated with that company. I can all do that all automatically, basically. And it goes over to email outbound campaigns. So if a marketing team wants to send emails, which is also very manual and very tedious work, you can also automate this process. So once you have built that list of my dream clients, I can basically reach out to them individually using automation systems. And the same goes for the voice agent, right? If I have a list of numbers that I scraped in the web, I can just let the agent call for me 24/7, which is pretty amazing. So what is the long-term vision of me as an agency owner, so to speak? I think about it really as an organigram. So me at the very top, as you can probably see, I'm like the top guy, so to speak, the CEO, who gives instructions or prompts to a specific agent that is then distributing the work across different, let's say, smaller sub-agents. So for example, one agent could take care of the communication bit, so email communication. The other one takes care of the customer chat support, for example, in WhatsApp. So you build all these sub-agents where in total you have like a full team of agents that work 24/7 for you. This is kind of the long-term vision that we have. And then apparently deploying these organizational flowcharts for all types of companies, B2B agencies, recruiting agencies, and so on and so forth. Right. Just one last case study. This is Navasta that I've been talking about. And what we've been doing for them is basically they were not on the radar at all on social media. And we've been using some of these automation systems to kind of churn out multiple posts on a continuous basis, made them omnipresent. And obviously they had a great product. They're very smart people. But we were the marketing agency that made them kind of omnipresent, and then obviously they were acquired by Autodesk a couple of months ago. Maybe you read the news. So what is actually Sonera doing right now? And for that, I'm going to play a video. I hope the sound works.
If you're an engineer, you and your team have likely spent countless hours with repetitive manual work. Even the smallest design change often triggers a whole chain of tasks, like setting up and running different analysis tools, processing results, and finally updating a report. All this manual work makes today's engineering inefficient and slow, leading to missed deadlines, suboptimal performance, and waste of valuable engineering hours. Imagine you could boil down these hours of manual work to minutes? Well, you can, with Sonera. Sonera's intuitive user interface lets you connect powerful CAD functionality, data processing, and all your favorite engineering tools into automated workflows, all by yourself, and without the help of programmers or IT experts. For example, import a geometry, set up a logic to clean up small gaps and details, and send it to your favorite mesher. Read load specifications and materials from Excel, and use them to automatically generate an FE setup. Run the FE analysis with a solver of your choice, and finally insert screenshots of the stress distribution into a PowerPoint. Once set up, this automation now runs on every change to your design, saving you hours of manual work. And while this is only one way Sonera can accelerate your work, our marketplace offers tons of integrations to automate exactly what matters to you. So start automating now to shorten project timelines, achieve next-level product quality, and ban repetitive manual work from your engineering process. With Sonera, the process automation for engineers.
So this was kind of a small introduction of what they actually do, and then maybe a, give me one sec, one quick demo. that works. Right, so this is the canvas. By the way, I'm not affiliated with Synera at all. I'm not making money off like presenting about Synera. It's just that I really think they actually don't have any competition in the market. So what they do is they really build this low-code language and deploy it in the automotive space, for example, and it helps engineering organizations to kind of capture implicit but also explicit engineering knowledge in one tool. So different departments drop in all the knowledge in Synera, and then basically what you have is kind of different nodes, a huge system of workflows that just works independently. And what you actually need is one champion or a couple of champions in an organization to run these workflows, which is super exciting. So what you can see is literally per drag and drop is you have item A and item B, which is just a bunch of numbers. You put in a multiplication node, and then obviously, as you can see, 5 times 5 is 25. And then what you want to do is basically generate an object. So what you will see in a bit is you can generate literally everything. Maybe I have to fast forward here. So what you will see is here's a sphere, and then you can, with the dragging sliders, adapt the radius of that sphere. So it's very intuitive to use. So this is just a very simple example. Obviously, this is not like like super sophisticated engineering application, but what you will suddenly see is you will be able to create a solid mesh, or even plug in an alter node that allows you to generate an even more refined mesh. So what you will see is here, you can literally with plug and play just define the element size, the max interior size. So whatever you want to do, you can connect it to this specific type of node that you can pull from the marketplace. So if you need an alter node, you get an alter node, and so on and so forth. It's pretty straightforward. You can obviously delete it. And then, let me just see. Right, I think this is the more interesting bit. So what you do right here is you define some input parameters. This is going to be very interesting. Some input parameters that you fix. You have an output that you fix, which is the area, and then the sphere, which should be visible, and something that we deploy now, which is Synera Run, which is very interesting because some of you might have heard about democratization. This was a very famous term in the simulation space. So SimScale was one of the first ones who used that one, which is basically you deploy a system or product or service that almost everybody can use because it's so easy, so intuitive for everybody. So even a designer would be able to do FEA workflows or build FEA workflows or run CFD simulations. So once we've defined the input, output, and the visible area, you deploy that workflow by sharing a link with your colleagues of another department. So they don't have to bother about this whole workflow thing that you've built, this humongous workflow that you've built, but you just give them inputs, the relevant outputs, and then the thing that should be visible, in this case, the sphere. And then obviously these people are then able to also share it with another department again. Let's say you define some input parameters and output parameters that are relevant for kind of building a system or like designing a system. Then you can just share that what you've input into the system to another department. Let's say the FE department, RFQ processes a request for quote, and so on and so forth. So it's very easy to use. The question now is, what has this to do with agents? So the question that I always have to ask myself as an engineer, how much of my workday in R&D is spent on activities like meetings, emails, drinking coffee, and so on and so forth. And when you do a survey, which is quite interesting, this is the typical engineer's day. I'm not sure if you can read it all the way behind, but 33%, so a third is spent on alignment, meetings, which is super annoying, right? You spend a third of your day in meetings. Then 13% is on socializing and coffee, which, okay, for some people more, for some people less, I don't know. And then 54% actually, so around half of your day is spent on valuable tasks, which is, if you're a CEO of a company, is not a great of a statistic because you want actually people to work on things that are meaningful and have impact. And then we have this here, very sequential, siloed, slow, and expensive processes. And this is particularly awful because if you think about the term China speed, so you have, for example, rapid economic growth in China. I mean, we all know that, right? It's not a secret. China is just time to market. If we talk about time to market in the automotive space of 2 years, and we're nowhere near close if we talk about the German automotive industry. Like 2 years is enormously fast. And you have to compete against China. And how do you do that? You have to produce better quality products in less time, which is obviously, as an engineer, this is a very hard task to achieve. And last, but certainly not least, you have hard constraints, obviously, on your headcount. So you have special experts, you have limitations in terms of resources that you can spend on your organization. And obviously on people and on talent, which is often there's a shortage on talent. And the vision, what I have as an agency owner, is kind of building Jarvis, the same vision that Synera has. So Jarvis, you all know Iron Man, right? Jarvis, that he prompts his agent, so to speak. He wants to have like a special material that's indestructible, whatever. Like he prompts it with a specific prompt, and then he wants to achieve a specific task X. And this is kind of the long-term vision. So we want to deploy Jarvis for engineers that is not like substituting. At some point, it will substitute engineers to some extent if you're not an expert, but at least include an experimentation layer on top of what's already running, right? It runs in parallel, kind of a, let's say, an R&D experimentation layer in the automotive industry that allows you to generate things much quicker than you've done it before. And what's really exciting about Sonera, and this is the reason why I wanted to present it today, is it's a low-code tool, right? And you might think it's something very simple to integrate. The problem is, though, however, if you have a simple simulation tool, a simulation software, for example, it's very hard to disrupt existing systems. So what you would have to do is you go into the automotive organizations, for example, BMW, Mercedes, you name it. It's very hard to tell them to change a system just because your tool is faster or runs 10x faster. You have to first prove the value and the ROI in order to even talk to them in the first place, and then obviously disrupting the existing workflow of like specific boundaries. So for example, your CFD tools sends data to the next department, it takes an input from another department. This is a very disruptive process, and automotive big companies don't like that. And what Sonera actually does, it tightly integrates into existing workflows because they have a marketplace where you can just pull everything that you need from the marketplace in terms of FE simulations, CFD simulations, measures, topology optimization, etc. So for them, it's very easy to already integrate into existing workflows, which is very kind of their big USP, and there's literally no competition they have. So how does a Sonera agent architecture look like? What you have to think about is what you see right here is a very simple is the large language model, right? We prompt something, which is the large language model in this case, and then you have kind of this weird thing called orchestration layer. It's kind of a short-term memory, a long-term memory, and some reasoning algorithm, right? And what you actually, the only thing that you have to do is you type in a user query, and I'm going to show you in a couple of minutes how that looks like, and you couple it with an add-on with the Sonera workflows. So basically, you prompt the Sonera workflow that you want to achieve a specific thing or generate a report in order to achieve a specific task X. And this is very simple to do. It sounds super complicated. Obviously, from an implementation standpoint, it's super complicated. But then you will save a ton of time and resources if you do that. Maybe one important note is, I'm not sure if Germans are here, but in German media, you will see that 1 in 3 companies, actually, there's a huge layoff, especially in the automotive space. So 1 in 3 companies, which is already a lot. So engineering companies, not only them, but also other companies, look for ways to save resources, which ultimately boils down to getting rid of engineers and keeping the ones that are specialists in AI. So I'm not sure if you've heard this saying, like, not an engineer will substitute you, but some engineers using AI will. So if you're not into AI yet, I would highly recommend you to get into AI, at least fiddle around with it, learn about large language models, what's possible with deep learning, large language models, and so on and so forth, because it will become very relevant. And if you work in the industry, it becomes more and more relevant. So if you're not up to date with what's going on in LLMs, deep learning, reinforcement learning, whatever, you should at least know the fundamentals, because if you compete against someone who already does it, it's going to be very difficult for you. I'm not sure, probably some of you are already working in the industry, so this is just a recommendation from my side, because I see it with my own eyes. Engineers being laid off because they're not really experts or champions in AI, so it's going to be very difficult for you to compete in the near future. If you remember what I said in the initial slides where I showed you kind of the long-term vision of Apex, it's kind of this organizational structure, right? You have someone who prompts the specific agent, so to speak, sub-agents. You can basically take that and transfer it one-to-one to the engineering organization. So what you want to achieve is you have an AI at the very top, obviously prompted by someone who knows how to use that agent, and then which basically prompts sub-agents who then prompt sub-agents who are very specialized in a specific niche. So you would have one agent being very specialized in FE workflows, the other one being, for example, an expert in PLM workflows, and so on and so forth. So basically, you're not only communicating to the special agents, or sub-agents, but they can also communicate between each other and share information, which is also very interesting. So you don't have to go to your colleague, drink a cup of coffee, talk to them for like 1 or 2 hours. You can just let the agents talk to each other, and you basically save tons of time and resources, obviously. It's a no-brainer. This is kind of a 4-step process of how we would actually deploy such an agentic engineering system. So you first start with a low-code approach. This was the short video that I've shown you. You start with the low-code approach. You connect it literally to any CRX tool that you want to, right? FE, CFD, and so on and so forth, whatever you want to achieve. Then you publish the workflow as a basically with scenario run, for example, and then you can enable the AI agents to control these processes. But I think, I'm not sure, how many people have worked, yeah, go ahead. Yeah, so basically what you would do is, the agent at the very top wants to achieve a specific task. So you query the prompt, or via a prompt, the large language model, which is then going to call sub-agents. So for example, if the large language model, the prompt would be, I need a specific report based on a specific component that I want to produce. So for example, what I have to do is I have to calculate how much the parts cost, how do I have to manufacture them, and so on and so forth. So based on my input, the agents would know which agents should be activated. So do I need the CAD agent? Do I need the RFQ agent, which calculates the manufacturing cost, etc.? It would be derived from the prompt that you give into the system. Yeah. Correct. Yeah, correct. Yes. I can show you after the talk already how I would do it in N8N. So the basic structure of an agent is always the same. So you have an input, you have an output, you have a memory, maybe a database that you, like a rack system. So for example, just a database that hooks up to the AI agent that you can then call in order to learn about a specific task or from documents and so on and so forth, requirements. So who has worked in this room with agents already? Or you, okay, good, okay. Good. I think it makes sense to maybe quickly differentiate the rule-based approach, AI-enhanced approach, and agentic approach, and why they're so different. So for a rule-based approach, and I don't want to read from the slide, I mean, you can basically read through it, but the big importance here is that what you would do in a rule-based approach is you want to achieve a specific task X, and you just say, I import my CAD into CATIA, I want to measure it with a specific size, element size, and then I run a linear FAE analysis, for example. That's a very rule-based approach, very straightforward, you know what you want to do, there's no fuzziness involved, it's very deterministic. AI enhanced is something, let's say, if we talk about Neural Concept, Navasto, all these companies that work on graph neural networks, right? You will build surrogate models, for example, on CFD surface field prediction, and you give them training data, you train your model based on specific training data, and then it would give you, for example, predict a stress distribution or a surface field model of a CFD result based on historic results. So this is not a straightforward task. It's a very expensive task, first of all, to do. You have to train your models, you have to generate the data, first of all, and it's very complex. It's not very deterministic in that sense. And then the third step, obviously there's a fourth step then where you would have AI swarms, where you have like multiple agents talking to each other. You have the agentic one. And for the agentic one, you have, it's basically like human-like behavior. So whenever you have, kind of as a rule of thumb, whenever you have humans involved in the decision-making process, it probably, or maybe might make sense to involve an agent in the system. Of course, there's some differentiation, it's not that straightforward, but whenever there's a lot of fuzziness, non-determinism involved, you would actually deploy an AI agent. So one example right here is if you gather, for example, inputs, this was one of your questions, and let's say you want to generate a report, an RFQ response. So what you want to do as, let's say, a supplier, you have to calculate what the parts would cost, and then obviously give that cost report to someone who would actually buy the parts from you. So the faster you are and the cheaper you are, obviously, the faster you can land the deal. So for me, as an owner of someone who sells these parts, it's very important to be very, very quick. Otherwise, I might lose the deal. And for that, you could use something like Synera in order to build reports or reports, for example, very quickly. Right, and this was one of the questions that we had. So we have very simplistic, like it's not super complicated. You have a user request coming into the agent. You prompt the agent with specific instructions, what you want to achieve. And then what I mentioned is this rack system, right? So you hook it up with the agent. That could be company knowledge and memory. That's very important. So you have to go back in time and think, okay, what have we done in the past? What could be optimized? And then communicate it with other agents, for example. So you have obviously the reasoning part as well. So you can analyze, deduce, plan, and infer specific things with that agent. What's very important as well is you have the ability to interact with any data using engineering tools. So as I already said, like you can hook it up to anything in the marketplace that you want to hook it up to. FE, CFD, topology optimization, and so on and so forth. And what's very important, this is also what I mentioned, it allows you to tackle non-deterministic and ambiguous tasks. So for example, when the outcome isn't fixed or really predictable. You don't really know what's coming out, and you actually want an agent to see what's coming out because there's so many different options. So it's not like 1 + 1 = 2. There's only one way. That could be a solution. So there's multiple different ways, very complex ways to achieve a specific goal. Then you would actually use an agent to come up with ideas, thoughts, plans maybe, to solve that specific problem for you. And for that, I can show you a quick video how that
We've
works.
all been there. You kick off a new engineering project with experts from design, simulation, costing, and manufacturing, and it's going well. But then, the progress slows down. For each design iteration, experts have to collaborate, but as they are also involved in other projects, get sick, or go on vacation, coordinating meetings becomes a challenge. In addition, project reports have to be written and read, causing further delays. The result is a low-efficiency process, leading to a shortage of design iterations, compromising optimal performance, and costing you your competitive edge. So what if you could get rid of these bottlenecks? With Synera and a network of specialized AI engineering agents, you can. These agents combine two superpowers. First, seamless communication with each other and your human team members via advanced language models. And second, the ability to run automated engineering workflows with Synera to modify geometries or evaluate mechanical performance, manufacturability, and cost. As the agents collaborate autonomously and around the clock, delays are cut down to pure calculation times, accelerating the project significantly. And better yet, every conversation, decision, and data point is documented automatically, providing full project transparency. With Synera and your network of engineering agents, your team focuses on big decisions while the agents handle the rest. Get the best out of your project timeline with generative AI and Synera.
Was that somehow clear of what we can achieve with agents now? It becomes more clear, right? So everything that's basically tedious to achieve and takes a lot of manual engineering work is something that we can solve with agents. And there's a couple of bullets that I brought with you. So why agents are the future? I think it becomes quite obvious, right? There's a couple of arguments for it. They can work all around the clock, right? So if you don't have to wait for, let's say, sit in the office and wait for the task to be finished, you can just give it to the agent and the agent would actually finish the task for you. This is the same thing that I mentioned in the beginning. Instead of manually scraping for customers online, I can just let the agent do it, the automation system, and then I'm basically done the next morning. There's no communication delays, especially when engineers talk to each other. I think the delta T between agents talking to each other versus humans is much, much lower. I mean, this is also quite obvious. And yeah, instead of like very tedious manual sequential processes, you actually shorten the time to market ultimately if you can release your product with higher quality to market faster. This is ultimately what all these companies want, especially in the automotive space. This is also what we discussed already, kind of multi-agent system. They can talk to each other. It's much more concrete now. You have a CAD agent, an FE agent, and a costing agent, which can talk to each other. So for example, if you prompt it with a specific query, let's say you have another CAD that maybe increases the radius of that sphere that you saw, the part becomes more expensive, for example, which is now quite obvious, right, if I say it. But let's say you have a multi-part system like a door assembly, for example. It's much, much more complicated, especially if a couple of parts change at the same time. It becomes very tedious to do that task manually. This is also one of the examples right here. So you take this and you apply it to a use case, which in this case would be the door assembly, right? You see, it's very complicated. If you do that manually, it takes you hours to do that manually, right? You have to adapt it. You're not supposed to make any mistakes, and if you make a mistake, it's going to be awful. There's a lot of second and third order effects if you make a mistake as a human. So you just, as a cost manager, you would prompt that cost manager, which then again calls sub-agents in this case, which is the CAD analyst, then we have the process expert, and then the costing analyst, which if you prompt it, well, I'll show you in a bit in the video how that looks like, it's actually pretty straightforward. Let me just see if that plays. So there's no sound. But what you will see in the beginning is there's the actual system. So this is the system of the door assembly. Not really exciting, not relevant for us. But what we want to do is actually we want to prompt that system. So we've deployed the system, and now we want to prompt it. We want to achieve a specific thing. So what we type in, hey, how can you help me? Question mark. And then obviously it gives you all the knowledge that it has about that specific system. It's pretty slow. So it's calculating, it's calling all these agents, the cost engineering agent, and so on and so forth. And then you have a summary on the left. So you can ask it about analyzing complete manufacturing costs, providing detailed cost breakdowns, manufacturing insights, cost optimization opportunities, and so on and so forth. Now, if you go to a human engineer, of course, they're experts on what they do, no doubt about it. But it takes you much more time to actually get what you want from that specific person. So the file path is here, so we give it the CAD path, and we want to achieve specific things. I need 1,000 parts of it. It's quite a lot. So you just prompt it, and there we go. Instead of manually calculating all of this or going to an Excel spreadsheet, whatever, it just calculates it on the fly, like in a couple of seconds. So fast forward, maybe. The video is quite long. So right here, right, you get the result, and then obviously you can take that result, and if you need a report, you can hook it up with a report agent, which is then going to generate a report for you that you can show your boss or, let's say, a customer, for example. So incredibly powerful system. You see all the breakdown, all the different agents that have been called. You can see BOP tools, so bill of process, cost analysis, cost tools, and so on and so forth. So you kind of get the point, right? So everything that's been tedious work up until this point can be automated using the agent. Okay, this is exactly what we've been discussing right now. So obviously you don't have to only work with these agents in the box right on the left, but you can also hook it up to the CAD engineer, for example, who, for example, would, I don't know, generate a new design, and based on that new design, you want to actually recalculate what the cost of that part is going to be. It's very straightforward. And then what we had is, instead of having that manual process, which obviously takes a lot of time, like keyword China speed, you want to just shorten the time of achieving a specific task X with a specific goal. Obviously, you want to save cost, resources. And ultimately, what people actually do, what I already told you, is they're getting rid of engineers right now. Right? If you're not an expert, if you're not the champion of using a tool like this, then they're already getting rid of you. I think what's also very interesting when I talk to a lot of companies is identifying a use case. I mean, AI is great. Everybody talks about AI. I'm not sure how long ChatGPT already exists. 2.5 years, maybe? Maybe correct me if I'm wrong, 2.5 years, roughly. I'm not sure, maybe longer. There's always the question of, we want to do something with AI. The question is why? And then I say, well, we want to jump on the hype train. But the question always is, do you have an actual pain that you can solve using AI? Maybe you can use it using a rule-based approach. Maybe you don't need AI in the first place. So the question always becomes, from a business perspective, but also from an engineering perspective and standpoint, do you actually need AI? And what is a good use case? In a nutshell, so I can actually finish the presentation now, but I have a couple of slides prepared, is always the crawl, walk, run approach. So you first start with a very niche down problem that you want to solve using AI. You prove value in that small niche problem first, and then you expand it. In terms of business, it could be you solve a specific task X in marketing or in sales. You solve it, you prove the CEO some value. What is the return on invest? Is there actually some return on invest? Because deploying the system is not for free. If you use Scenario, for example, there's a cost associated with it. There's time that you have to invest to train the engineers, to make them a champion of, to use that tool. So there's going to be kind of first an investment, and then obviously at some point you're going to be break even, but how long does it take to be break even? And how big is the return on invest? You need to think about these things, because I think you can automate anything. And if you're a little bit in the AI agent space, you are definitely in that space. If you go on YouTube and you look up AI agents, people want to automate everything. Up until the point where you have to remind yourself, what is the birthday of my mom? They would still automate it. Like, it doesn't make sense at all. And if you really have to think, you have to think really deeply of what you want to automate, and if it actually has impact. If it doesn't have impact, it doesn't make any sense. From an engineering point of view, but also from a business point of view. Right, okay, that music was not supposed to play. So there's specific frameworks that you can use, and this is one of them. There's obviously multiple frameworks that you can use. First of all, what is the business impact? We talked about this. How scalable is the solution? How suitable is the solution? And obviously the implementation side of things. So how long does it take from an implementation side of things? How many people do you have to use to run that first use case, etc. In terms of the business impact, this is also what we do with customers, by the way, is you first lay out the process, this is a very simple process, by the way, on the right side. So you lay out the process of how a specific task is going to be represented as a flow chart, basically. It's a very simple flow chart. Some processes are much more complicated than this, especially in engineering applications. And also if you have multiple stakeholders involved. So you first have a blueprint or kind of a flow chart of what you want to achieve, and then you want to see if you can actually digitalize that flow chart, if it actually makes sense. Keyword was return on invest. So for the automotive industry, for example, it's for them very important. Time to offer, what's the win rate, what's the sunk cost, and what can I actually optimize? Like what's in for me? If I invest 50K, let's just give a rough number, it's not going to be 50K. But let's say, depending on the use case, let's say 50K, when can I get my money back? Because I'm going to be in minus, so I want to prove the value, right? Why would I invest 50K in something that might not even have any value just for, I don't know, for investors to say I'm using AI, right? Doesn't make any sense. Right. And then high frequency is very important as well. If you do a task not that often, it doesn't make sense to automate it. If I call a person once a week, I'm not supposed to build an agent that calls a person once a week. Doesn't make any sense. It's not scalable, right? But if I call 100 people a day, continuously, let's say 24/7, 1,000, I don't know, then it makes sense to actually deploy agents, let them run in parallel, and so on and so forth. You get the point. And then what's very important as well, maybe if you build an AI use case, such as a report generator, maybe that's relevant and very interesting for the FE department, right? You have FE reports, for example, very important, let's say, what is going to be the stress distribution on a specific part, X, right? But then obviously you can take that report generator and apply it to other departments, the CFD department, the CAD department, and so on and so forth. Because you want to generate reports ultimately. In report generation, it's actually a fun fact, maybe not a fun fact. It's one of the most tedious things to do, and people don't automate it in the industry. It's actually crazy if you think about it. People don't automate report generation. Some of them do, but most of them don't. They just have an Excel spreadsheet or some very old process from 50 years ago that they still use, but it's been convenient up until that point, so we're not going to change it. And once you see it, you're going to be like, why are you doing that? It doesn't make any sense, but people don't want to change a running system, which obviously makes it very hard for companies like Sonera to have them adopt a new solution. So there's also a lot of activation energy that you need as a company to convince people why AI makes sense or agents make sense. This is the same thing again, maybe with a small animation. So what I've shown you in the video before is just a multi-agent system right now of someone prompting the agents, right? He talks to his little agent buddies, and then the RFQ manager is going to be called. So RFQ is a request for quote. So how much of that thing, how much cost is involved in that specific thing that I'm trying to produce? And there's multiple agents, the CAD analysis agent, and so on and so forth. And it would even be able to analyze potential problems even before you do the next step, which is super cool. Then next one, we have the scalability, which I think is also a no-brainer, but I'm saying no-brainer, but the thing is most people really don't take it serious, right? If you can use an agent for one use case, it would make sense if other teams could also benefit from it. I just mentioned reporting, but there's a lot more, right? And the first case could be used as a blueprint for R&D purposes for other departments. So even though the AI use case might be a little bit fuzzy, it's not really clear if it still provides some value, maybe other teams could still already benefit from it. Give it to them, maybe build 1 or 3 champions in that department and let them play with it on the side and run some experimentation layer in parallel of what they're already doing, which is also is actually a no-brainer, but nobody does it. And then reusing individual agents. This is also what I talked about. If something works, just you do some transfer learning to another application. I think this graph is pretty interesting because on the x-axis you see kind of the task fuzziness, rule-based versus human-like, and then the autonomy level on the y-axis. And if something is very rule-based, I've talked to you about it already, like you want to do a linear FE analysis, it's very rule-based, right? You do this, then you do this, then you do this. But the more fuzziness is involved, the more non-deterministic a workflow is, the more solutions there are, the more complex the workflow, the more it makes sense to run these agents or deploy multi-agent systems that can talk to each other. Right? Sometimes it doesn't actually make sense to deploy agents such as for a linear FE analysis or a simple CFD workflow to have some first calculations how the flow behaves. It doesn't make sense to use an agent for that specific purpose. It's just wasted resources. This is something we've talked about already. Yeah. For example, it makes sense if the human in the loop can change the order of a specific task. So let's say you have the rule-based approach. First you need the CAD, then you mesh it, and then you process it, and then you have the output results, so you post-process the results. In this case, you can't really switch these tasks, but if you have tasks, for example, where it's necessary or sometimes it's mandatory to jump back or go a step back and, for example, check the cost of a specific part or do anything else, maybe that's not planned, what a human would do, then it makes sense to deploy an agent, right? An agent is very agile, it can do specific things in an order that's maybe not deterministic. So from an integration level, from micro to macro level, this is how it would look like. You first, for example, have something very simple in air quotes, such as a reporting. And then you go basically down from a very low-level approach of like as simple as a reporting thing, going to the processing part, the pre-processing part, up to the macro level where you actually build the full system and put it together. So this is kind of the division, something that you can build already in Sonera. Like you go from something very simple, a small problem, and then you can assemble all these parts into something which resembles a full system. And then obviously, this is something I talked to Luis about, something like a marketplace is also very interesting. So whatever you need for your application, you can just pull. So you see a couple of nodes, Abacus nodes, a CAD node. You can even use a SimScale node if you want. So everything that's in the marketplace that's relevant for your engineering applications, you can just pull from it and build an agent on top of it. And in terms of implementation guidelines, so the crawl stage would probably be 3 stages, so you have 1 to 3 month projects. Everything less than 1 month actually doesn't make any sense. So you need to give yourself some time to experiment. You need at least 3 people, I would say, in big organizations, minimum 3 teams. If you're, let's say, a smaller business, probably 1 or 2 people. And you need to have a champion in the organization that knows the process end to end. It doesn't make sense to talk to someone who knows the process so half-baked. He knows it roughly, but he doesn't actually know it end to end. So you need people, this is why also you have 3+ people, that sit together, know the process end to end, and can then digitalize the whole process and fully understand it and deploy it. Okay, summary and key learnings. I think we've been pretty quick so far. So, what do we have? Basically everything I said, right? If the task is on a critical path, it might make sense to use agents, also in order to save resources. It should ideally be reusable. It doesn't make, in most of the cases, it doesn't make sense to use it for one specific task. If you have some fuzziness involved, it's a very weird term, but if you have some non-determinism involved, it makes sense to deploy agents. And my recommendation is, as always, also the recommendation of Sonera. Start now, but start small. Because AI is going pretty quick. If you are in the space, you know, it's going much, much faster than expected, and keeping up with the changes is very hard to do. So yeah, I would definitely pick a specific use case, start with it, and just see how it goes. So yeah, that's pretty much it.
Thank you, Jousef. So, questions from the audience?
So thank you so much. So you're talking about the marketplace in the end, right? How do you see that, you know, this automation and even the agent automation will play in terms of how actual engineers will work, not just as operators in a workflow, because obviously, you know, a lot of that will be automated. So the trend will be having less engineers working on the workflow, but do you see that then engineers can probably work on the leaves of the workflow, so on the actual nodes that will be part of the workflow? So there's going to be maybe an engineer that's just responsible for a certain type of simulation that he sets up really well, and then that becomes a point in the marketplace.
Does it work? Yeah, okay. What we see in the industry right now, because we work with so many clients who actually deploy these systems to automotive OEMs such as BMW, etc., like big organizations. So what we see is there's always a couple of champions in the industry who use these specific tools. I think there's going to be these people who use the tools, but I think your question was more related to...
More related to the, let's say, the role of the new engineers, right? That instead of being assemblers of the workflow, right? Of workflow of a big engineering process, end-to-end, look at several stages. They're probably going to become more focused, like a specialist, on a certain component of that workflow, and that component of the workflow will be a piece in that marketplace that then gets pulled by agents and all that. So let's, for example, let's suppose that I get really good, I build my own software, and I get really good at simulating, let's say, how glass breaks and I have that function, that software that I built. I'm really good at that, right? And then I push that to the marketplace so that it can be picked up by agents that, you know, as part of some process, have to test the resistance of a certain component.
Wouldn't it actually be an argument for becoming more generalistic? Because you don't have to be an expert anymore. You can just be a generalist who knows how to remote control these tools, because you need to know about LLM, AI in general, the specific simulation tools, etc. So I think the engineer needs to be more like a generalist rather than a specialist. Of course, you need still the specialist to solve very, very specific types of problems, but I think the trend moves more towards now being less of a specialist, but more like a generalist, is my observation at least. I'm not sure if someone disagrees, but this is my observation. This is also what I do, right? Like if I want to learn about a specific thing, I mean, Ricardo had a very, very technical talk. For me, it's probably more important, like what is possible with deep learning and like these SHAP models, etc. But I don't really need to fully understand them in order to be like to talk about it. This is how I see it. So for me, it's fine if I know some things very well, a little bit of, like a lot of things very well, but not like super, super deep, not like a pie-shaped personality.
Yeah. But my point is that it actually opens room for both sides. So it does lead to some opportunities for generalists. I agree with you. So you can operate on much more complex systems because you don't have to know the details of everything. So you can use these agents to help you assemble complex workflows. So I agree with that. So there's room. So it grows that side, but I think it also will grow the side of, hey, I'm just really good at one thing, right? I chose to be a specialist, and now I have a way to monetize my specialty because I can build a small component that I don't need to sell door to door. I can just put it in a marketplace and it will be picked up by agents because it's very good at one thing, but that can be automated. So
okay,
I
see where you're going.
Both ways.
Yeah, both ways, definitely. Yeah, I see where you're going. Makes sense. Yeah, I see the same thing. Makes sense.
Yeah, I'll bring you the microphone.
Hello. Very much you are talking about, you can call it soft engineering versus hard engineering, or saying, we can look at, take an example of a CFD code. From the point of view of the user and the point of view of developer, there are two different fields. And I ask you, is there room for the users? Is there room for the developers who's going to write the actual code? Who is going to do the hard engineering? Who has to know the mathematics, the physics, everything that goes with that?
I think definitely, yeah. I think there's room for both, as Luis just mentioned. So you have the end users that I think...
No, but I'm seeing the world of the art developers and the one who do the actual code and put the mathematics and do the transfer of all the mathematics into lines of code are becoming less and less people. If you take the example of the CFD codes these days, nobody develops a CFD code from scratch. They could just go to OpenFOAM and pretend to be a CFD knowledgeable person.
Yeah,
I'm quite sure this happens with many other areas of many other fields of engineering. And this border, this is where the mechanical engineering or the electrical engineering ends and starts the industrial management or the engineering related. The difference between engineering and management is becoming a very difficult border.
I think, this is just my opinion, by the way, I think there's always going to be room for both. We just had it with Luis, right? Ultimately, the end user really doesn't care if they can use the tool, they really don't care about the implementation. This is what I see, right? Tools like SimScale, for example, they made it pretty popular, the topic of democratization, that even someone who is a CAD specialist would be able to run CFD simulations. Now, all the engineers who were technical experts in CFD got all offended because how can a CAD analyst, how dare you run a CFD simulation? Because he's not an expert, right? I think there's always, you have to see the side of the non-expert who would like to tap into these kind of areas, right, and wants to experiment and see what's coming out. But on the other hand, of course, we need the deep technical experts, the academics who work on these deep research topics in order maybe to improve the underlying architecture of what we are then using as the lazy users, so to speak.
Yeah, I think the difference is on knowing how the car works and how to build a car and how to drive a car. So you go to the school and take a driving license and you don't know very much about the mechanics, but you still know how to drive the car safely. That's the point these days. But here in a school like this, what we have to teach the students, to teach them to be hard engineers working on the hard side of the engineering or on the soft side of the engineering.
Yeah, I think it's going to be much more complicated for the engineers. When I think about my dad, when he used to study, it was like less complicated, and almost, I think, no programming involved. And nowadays, the engineer has to do so many things, so many topics, so many things they have to know about. So I think, of course, as you said, like the hard engineering skills, but also the soft engineering skills. You need to develop both. And I think the ones that I know that are most successful have both. Have the hard skills, but also the soft skills.
Yeah, but the time is finite. You have 24 hours a day.
Hi, I have a question on the responsibility of this AI. What happens when there's a mistake? Like the engineers could say, oh, the AI made a mistake. What are the regulations in that part? Like, and if there's an accident, there are lives involved. Well, we didn't know the AI made the mistakes. So who's responsible? The AI company, the engineer who used the model? What is the, like, there's a lot of talks about regulating AIs. And yeah, if you could shed some light on that issue.
No, very good question. I'm not an AI ethics expert. You probably need to ask some expert about that. But my philosophy is always having a human in the loop. Like, let's say we build these end-to-end workflows. Let's say a very weird example. You probably cannot relate to it at all, but let's say you run ads. Like you run ads on Meta. For example, you scroll Instagram, you see an ad, right? For example, what we do with these workflows is we run specific ads. We want to achieve a specific task for marketeers, for salespeople. There's always at the end one node that prompts the human that, by the way, this task has finished, please check it. So there's always a human involved in order to check the output of the system in this case. When we talk about autonomous driving and so on and so forth, this is a whole other topic. But for these type of low-code systems, it's very easy to, at the very end, have one node that just says, hey, by the way, it's finished, please check it.
But me as an engineer, I would be taking the responsibility of any mistakes made by the AI. By using the
ultimately
product.
You sign it off, right?
Okay, so it's the user who signs off all the responsibility.
Yeah, ultimately it's a user mistake then. If you make
okay.
Because you have to check what's the output. If the output, let's say the stress is too high, but you're going to say, well, AI said it, so I'm going to be cool with it, then obviously it's your fault because...
Okay, so it's like any other tool.
Yeah,
say.
Exactly.
But
exactly.
The user has to accept the responsibility of any mistakes made by the AI that the user does not catch. So the user would become like a error checker for the AI.
Correct. And I think it's becoming a synergy. So engineers plus AI, where the human or the engineer just checks the results, or kind of remote controls the agents or AI, and then just has to check what's the output, and then makes decision based off of that. This is kind of my vision. This is also how it works in the industry, literally one-to-one.
I do feel more comfortable about checking results of calculations that I made.
Makes sense. I would do the same thing. I would do the same thing, yeah.
Hey, well, I'm Guilherme Vaz. I'm also CEO of startup, but I'm an engineer also. Okay. So you spoke about agents substituting engineers and making the process much more, efficient. My question, as a funny question, is: can AI agents also substitute the CEOs? Because we are saying substituting the engineers, but there's much more process that can be improved and maybe even better. So I think as a CEO, I'm less important maybe than all the engineers I have. So what is the borderline for this?
That's a very good question. So what I do, for example, is I prompt an LLM of giving me advice how to maybe do a specific task, but I don't want to remove myself from the equation, if that makes sense.
Yeah, but we are doing that with the engineers that are under.
Yeah, the question is though, not all engineers are going to vanish, because if you kind of fast forward that theory, it would mean that all engineers are vanishing, which is not the case. But you have specific experts who know how these AI systems work and how they are supposed to be prompted, so that ultimately there's going to be a pinnacle of engineers that knows how to use these systems.
Yeah, but they're also the guys, and I think here the professor said, they're also the guys that develop the tools the AI agents are running.
Yeah.
So I think what you said, and it's true, some of these engineers, and you said also maybe in the beginning, will be other kind of engineers. So you still have the guys that develop the tools, you still have the guys that develop the AI agents. So at the end, maybe we'll have some other kinds of engineers in the future. But and maybe also other kind of CEOs. Maybe we don't need a person CEO.
Yeah, go for it.
Question.
I think AI can substitute the CEO and kill the company even.
Okay, I'll accept that, that's fine.
I have another question, it's more technical now. You said there's this scenario that I didn't know, doesn't have competition. So, well, 15 years ago, we were doing things, I came from the Netherlands, which was with Rhino and Grasshopper.
Yeah.
And we were automatizing everything in Grasshopper.
Yeah.
And it was not AI agents, but it was the typical Grasshopper kind of language. And the communication between all kinds of tools was automatized. But it was only for some specific process. So what you showed here is for huge companies. I mean, a small company, do they need all these things? Because even I was working in a big institute, we automatized the CFD calculations for a submarine, for the Dutch Navy, all in Rhino and in Grasshopper. So is this not the nuclear bomb to kill the fly? I mean, for big companies you can use it, but for small companies, do you think small companies will use this kind of so advanced, can do everything?
But I think first, most companies...
Thank you.
Yeah, thanks a lot for the question. I think most companies would probably try it first by themselves, and if they see there is some value in Synera, obviously you wouldn't just deploy the system, you would just do a proof of concept first and see if Synera actually makes sense for them. But I think for the bigger one, obviously a no-brainer, because what you have is, talking about substituting the engineers, you have implicit and explicit knowledge of the engineers built or baked into the system, right? So for the companies, for the big ones, it's very easy to say, hey, by the way, dear FE analyst, all your knowledge is now in this low-code system. We don't need you anymore. We have someone who's a champion who knows how to run the workflow, but now you've built it for us, so we don't need you anymore, or we need you for something else. I think for bigger ones, it definitely makes sense as a bigger return on invest. For smaller ones, probably the return on invest is marginal, I would assume. Obviously, there are some cases where probably it makes sense. This would be, by the way, Grasshopper is the fundament of Synera. They come from Grasshopper, so okay. This is what I know from the history of Synera. So that already existed. It existed, but not in that way. Yeah. We use Grasshopper. Yeah, that's pretty cool. Good catch.
More questions from the audience? So I have maybe another question. So, you know, at Inductivo, we developed this API where you can call a series of open source simulators. And a natural way to benefit from large language models that could be encapsulated in a small agent would basically be at the translation of a natural language specification into the input files for the simulator. So, for example, I want to make a simulation of a car that looks like this on a wind tunnel, or I want to simulate and run it on OpenFOAM, or I want to simulate this wind turbine with this height or whatever on an offshore location with waves of I don't know how much height, and use, let's say, OpenFast or something like that. So from your experience in the industry, how far are we from having perhaps specialized LLMs? I don't know if they have to be specialized per simulator, to be able in that to perform well in that translation task, right? From natural language to specific configuration files from a simulator.
Are you speaking out of hope or fear? Okay. Okay.
No emotions involved.
Okay. I think it is still for the organizations, for classical B2B companies, automotive OEMs, it will take some time, because if you believe it or not, even if you talk to a CTO of a big company, you would assume that they know how AI works. But the problem is you have to educate them on what's possible with AI and what's not possible with AI, because sometimes they might think you come in with a magic pill and solve all the problems they have, and suddenly you sell 500% more. This is kind of the assumptions they have, so you have to educate them of what's possible. And I think LLMs are not that obvious and not that common in the industry yet, but it's coming, slowly but surely.
I just comment on what Hugo said. Yes, we are doing an LLM just to learn from CFD calculations. So it's a research project where, in fact, it's with Refresco is our tool, but also with OpenFOAM. You talk with them, and it does well. We want to achieve. We're still not done that. That exactly like that. I want to compute this turbine in Viana do Castelo with these waves, and it does the setup for you. So there are people working on that right now, and we are in one EU project that doing that.
How big is your company?
We are small. We are 20 people.
Yeah, okay. For smaller companies, it's much more straightforward, I would say. For bigger corporations, it takes a lot of time.
No, we are all R&D company. We are an R&D company, but this is not for a company. This is in a consortium of other or institutions doing this. So there are people in Europe trying to do that. You know, specific LLMs for specific applications, and in our case for CFD. Yeah.
We need to give you a slot for a second talk about that. Okay, any other concluding question?
If you have some free time, by the way, I highly recommend you playing with N8N, by the way. So you can download it maybe today, make an account, not download, but make an account and play with N8N, just to understand how agents work, build your own agent system. I think it's very interesting. Also for all the engineers here, whatever you want to build, if you have an idea, just do it. All right?
All right, so let's thank Jousef again.
Starting at 1 p.m., I now invite you to join us at the coffee lounge for the lunch. Okay?
Okay, welcome back everyone. It's my pleasure to introduce Guilherme Vaz. He's currently the founder and CEO of Blue Oasis. Super interesting startup, a small company based in Portugal, actually in a lovely location, Ericeira. If you like surf, you might have heard about it. Where they do extremely interesting research at the intersection of numerical simulation, machine learning, and even hardware. Right?
Yeah.
Prior to that, he was a researcher in the Netherlands in the Maritime Research Institute, and he has a PhD in mechanical engineering from Instituto Superior Técnico in Lisbon. So, Guilherme, thank you so much for being here. You have the stage.
Well, thanks, Hugo. Thanks, Luis. I think I'm very proud of being here and proud of being a company like Indutiva. So we have to change the realm on Portugal. We are in university, but in fact, I think there are some smart companies like Indutiva, and let's be a little bit blunt, us trying to change the landscape of innovation in Portugal. So I'm very happy to be here and also to be so-called partner, I think, of Indutiva. So today I'm going to, first, I never had almost 50 minutes to speak. Normally I pitch for 2 minutes as a startup CEO, or 10 minutes in a conference. So today I have 50 minutes. So it's like a dream for some guy like me that likes to talk. So I'm going to introduce, please bear with me, 2 or 3 slides about what we do, all related with everything that we have heard today already. And then we go to this EU project that we did that is called exaSIMPLE, where we want to combine, in fact, some of the areas we work. So in fact, combining CFD and AI, different than what we have heard today. So most of the things you have heard today is a little bit different, but you will see that these sessions are well organized because you see some similarities. So we are Blue Oasis, so we work mainly or exclusively in the ocean. Everything related with the ocean, okay? If it's in land, we don't do anything. So we already can breathe more than 2 minutes underwater. So who knows where is this? Somebody knows? No? It's Azores, yes. So I don't know if this works. Yeah, so this is Fayal Island. So this is our new offices. They are going to be built here, and we have a house there, and this is what I call the Pirate Bay. So it's Porto Pinho. So Fayal is one of the 9 islands of Portugal, and where we have an office for testing all the hardware / AI / digital twinning solutions. So we do most of the intellectual work in Ericeira, and all the experimental work and assembly in Azores. And it is really nice, as you can see. So it's the Portuguese Hawaii with more rain. So one slide summarizing Blue Oasis, okay? So we work in the intersection of HPC, high performance computing, on big data. So here I include numerical modeling, on big data generated both by numerical modeling but also by sensors that we are also having. And once we have big data, numerical modeling, and heavy computational resources, we started already, maybe when I was in the Netherlands already, 8 years ago, thinking on going towards the machine learning. So in fact, this is the sweet spot. This is what they call the industry 4.0. So you have high performance computing, so the numerical modeling, they are not going to disappear, guys, okay? So we have the AI and ML, and we have heard about it, and we have big data. Not only numerical data, we need real life data, and that's where enters here the edge computing, the IoT, the sensors, okay? So we work there. And which areas we work? Well, we started with a lot with renewables. So wind energy, wave, current, floating solar. So this is also because of my background. By the way, I'm an aerospace engineer from technical, and then I did my PhD in the Netherlands when there was not normal the PhD in the company. So I was doing the PhD at IST, but I think I only defended my thesis at IST. I was always in the Netherlands. Okay. So it was already this kind of PhD in the company. So I'm an aerospace engineer with a PhD in acoustics and naval architecture. So you see here work for renewables, work for naval, so Navy vessels. So this is a ship of a big Northern European company. We do studies on superstructures to see interaction of winds between ships and drones, or between even just the drag around big superstructures. This is propellers. We also do analysis on propellers. So this is the typical numerical modeling. For that, we need bigger supercomputers. On the right, you also see some CFD calculations. Let's see if this works again. So what you have there is, should work, but what you have there is acoustic simulation, so underwater propagation in an exercise organized by the Navy, Portuguese Navy. There is acoustics, underwater acoustics. Here it's a wind turbine under imposed motion. This is with CFD codes. This is code from one of the main developers here, City. This is Reef 3D. A paper we did together with them in order to check if the waves are surfable or not in Ericeira. Okay, you go to WindGuru, that doesn't work. WindGuru has 1.45 kilometers, guys. All the beaches in Ericeira are less than 5 kilometers. So we had to downsample to really compute nonlinear waves to see if they are surfable or not. Continue to go to WindGuru, and then if you go there, as you see, a lot of tourists go there to have courses of surf, and there's no waves. So you needed to downscale really per beach to see, to help the guys there to see if the waves are surfable or not. Otherwise, they can lose a lot of money, or the tourists are also mad. So this is one of the beaches, is Ribeira de Ilhas, if I'm not mistaken. And last but not least, so we do also sensors in the water. So what you see here, and there are fishes there. So these are turf waters, what it's normally in our ocean. And we are doing things related with the ocean restoration, also conservation and AI for species detection. So detecting the fishes, see how big they are, see the weight, see patterns, they are sick, they are not. So you see, we're combining numerical modeling and AI, very industrial approach. So it's a little bit different. For instance, the first talk of Ricardo was very, we need those things, very academic. We are really here in the other extreme, close to the industry. And last but not least, we are doing a sensor or something smart that combines everything that I will talk later. So a company without people is nothing. So I always present the guys that work with me. So we are around 17, 18. So this is the company. And we have we have 3 PhD students. And this is not positive discrimination. It just happened like that. I don't know why. There's a physical explanation, really a physical explanation. Is that we are doing a lot of acoustics work, and we need to do AI for identifying things in the water. And women listen much better than guys. So there's a lot of sounds, especially low frequency sounds, that the guy cannot hear. And women, for instance, when you have a whale, that they equalize sometimes the very low frequencies, I'm looking to that stuff and I don't hear anything. And and especially young girls, they can listen to everything. My girl listens to everything, and I can be looking to that and seeing the spectrogram, when I see there's a whale, listening, nothing. So in fact, women should be better submariners than guys, you know? So, and there's a reason why it's just happened like that. They all, I'm speaking Dutch now, that's all volunteers. So we have a bunch of girls from high school, university, helping us, listening to whales, you know, listening to dolphins, listening to vessels, and labeling for supervised learning, okay? We need still people in the loop for supervised learning. So we are in Ericeira, we are in the Azores, so our office is here close to the harbor, so really behind the stuff, so we can put the stuff. We have a ship, and then we go to the ship, and we do our operations. So all this canal Fayal Pico, this also there is fully instrumented with sensors. We get the data, we label the data, we ingest in some AI stuff that I'm going to show. So, but nothing that we do cannot be done without high-performance computing. And that's where I think we connected with Indutiva. So this cluster here, it was a cluster, I don't know if this one, I think one of these I was building in the Netherlands before my previous life with some guys. So already since 2000, I was working with Sarah. There was the Dutch supercomputing center. And so when I came to Portugal, there was even not Docano, there was Bob, there was Second from Stampede in Texas, the Texas Computing Center that I used when I was also in USA for some things. So there was no high performance computing in Portugal. Docano is quite good. It's starting, Portugal starting. But as a company, we needed these things. So we have a cluster, really ours, not in the cloud, not virtual machines, in Iceland. You can ask me, Iceland? It's quite cheap in Iceland, which is kind of strange to say that in Iceland something is cheap. But because the cooling is for free, and the electricity is for free also in Iceland. And the heat that we make from our calculations warms up the villages around it. So the cluster in Iceland that we do for commercial purpose, it's the cheapest I've ever seen in Europe or anywhere else. It's less than 1 euro cent per CPU hour. Okay? So then we have research clusters that we can use with you guys, students, PhDs, as long as we publish, being the Navigator in Portugal, and Iridius in UK, where I'm invited professor, and the Docano, which is, you have to apply for it. But last year in Docano, we got 13 million core hours for doing exaSIMPLE and for doing also AI. So all these things we are going to join, and we're going to send and make a cluster in the Azores. So we're going to make a private HPC center in the Azores. So one of the things, so you see that we do numerical modeling, we do acoustics, we do AI also. So one of the things that we were doing a lot was underwater acoustics, and we started to devise something based on our project that is HydroTwin. So it's a real-time underwater passive acoustic system. It's something like this, well, this size. And you can put it underwater and you detect everything that makes noise underwater. And there's something that we needed for a project. We needed to do something with acoustics for an offshore wind, and we devised something and we saw there was traction. So we took it out from Blue Oasis, we had a spin-off, and we were invested. So this is the HydroTwin, and it works with edge computing. So it's very nice to do AI, and it's very nice to do AI in a computer and a supercomputer, but at the end, to make something that works underwater, it's not so easy. So it took us a long time to make all the AI algorithms that work wonderful in our computers to work fast. So we have something, the edge computing, we send the data to shore, we have the AI algorithms with all the sensors we have in the Azores, it's low power consumption, you can make it in a buoy, you can make it in a glider or in an underwater vessel, and you can also let the people to train their own algorithm. At the end, what we want to do is something like this. So what you see is our acoustics model. When you see all the ships that are passing, the ships have a GPS in this case, but we want to do this without knowing the GPS of the ship. So imagine it's a whale, or it's a dolphin, and they make sound, and we're going to make a digital twin of everything that is underwater. So we can make a map of things that makes the sound, being these sensors, the ones that bring the data in order to make this. So this is supposed to have sound, so you have to trust me. It's not my problem. So what you see here is what's happening really underwater. So you have a file that is a file that you are listening, that we pass to a spectrogram, and then you're doing typical CNN complex architecture, but a typical CNN, where you are identifying in real time. If in this case, it would be nice to hear, to be honest. You have a vessel, and we have a dolphin, and a common mortal, we cannot hear. Maybe some of the girls here can hear, but the guys, you can forget, you cannot hear. It is not a joke, guys. It's like that. I'm sorry, we are not the strongest. So, can I take out the sound? This is really frustrating. So this is what is being done in the system underwater. Okay, so we are detecting, we send the data to a dashboard, and you can really identify automatically what you are. So imagine there's a ship without AIS, some military applications, some illegal fishing, refugees, smuggling drugs from Colombia, all these kind of things. So what was the trick here? The trick here is to have our own data, and the trick here is to use less than 3 watts of energy. So it's not so easy. It was tough to pass from a big computer to 3 watts, and the algorithm is also ours, and that's what we are doing. So now coming, a lot of projects, so we do services, we do products, we do R&D projects, especially with the EU projects, and so we are in two big projects. This is Pharos and Float Farm, all related to the noise and AI, and one of them that we also doing is this exaSIMPLE, which is the combination of CFD with AI, and that's what I'm going to speak about it. So I just wanted to give an introduction what we do. We do also products, we do only things related with the ocean, we have an AI team, we have an acoustics team, and we have a CFD team. And this project, exaSIMPLE, joined the CFD team and the AI team. So I didn't know if you guys knew about CFD or not, but okay, you saw first presentation. If you understood, you are experts. Ricardo, you are listening to me, so if you understood the first presentation, 50%, then you understand this. So this is some typical applications we do with CFD. This is real project. This is industrial project. This is not calculations in a square. This is a ship and a submarine operation. This is a propeller, and yes, cavitation makes noise. And this is more academic, to be honest. This is a scale resolve simulation for a high Reynolds number. I think Ricardo uses this stuff for these calculations to use the deep learning to get these coherent structures. But this stuff play a role, for instance, for long cables underwater, like when you are at a pipe, when you have risers, when you have anything, a mooring. This all happens in cylindrical structures. And imagine they are flexible, it's even worse. So these are practical things, very high Reynolds number. In the water, we're talking about billion, the Reynolds number. It's more difficult than going to space, okay, in the water. And so very high Reynolds numbers. And so what we want with this project, exaSIMPLE, is to make these calculations faster and adaptable for the new machines, for the exascale. Okay, we don't have any exascale machine in Portugal. We'll have one in Europe, but we'll go into that. So another thing, I'm going to speak about this. So NASA was one of the first institutions in America that pushed a lot for the CFD, already in the 60s and the 70s. And in 2015, they made a roadmap about NASA CFD vision for 2030. It was funny that in 2015, nobody spoke about AI, right? Or spoke about AI, but not AI applied to engineering stuff, you know? Of course, this AI statistics in steroids. So, but if you see here, there's nothing about AI until they had, in 2020, they had to review a little bit what is the roadmap. But in these huge CFD tools that you see that do in the industrial calculations, cars, airplanes, computers, trains, everything is using CFD for design or for optimization. You can improve some of the parts of the solvers, you know, to make them faster or to make them better. So one of the things is what Professor was today talking with me, is saying, doing nothing. You're waiting the computers get faster, and the codes get faster, possibly. It's not always like that. So HPC, they're talking about petascale, wow, in 2015, okay? But that's a mobile phone, almost. And then we are talking about exascale. They were saying exascale in 2000, I would say 27, 28. So we already have exascale computers. So these have to be adapted fast. And you can do things by improving your codes to the HPC. You can also do it by improving physical modeling. That's what Ricardo was showing today. How can we improve turbulence modeling? If we improve turbulence modeling, it's more accurate. Maybe we have to do then we get much more for each computation. So it's this one. Algorithms is what I'm going to speak about today. So in this Exascale project, we try to do connection of this HPC with changing the algorithms and using AI, which is not here in this NASA Vision 2030 for CFD, because they didn't predict that ChatGPT was going to boom, and then everybody started to use AI from all kinds of things that we have heard today. So the exaSIMPLE project works on algorithms and HPC, not on the rest. So exascale, just for the definition, 1 times 10 to the power 18 floating point operations. There is the first exascale computer. It was Frontier, that I think it's number 2 now, but it's El Capitan. This is from Department of Energy in America, and also NSA and Lawrence Livermore. So these are all exascale computers. These Aurora also exascale computers. So our Azure kind of things, it's not. And in Italy, which is funny to see, Europe was always not so far. This is a website called Top 500, where you see all the fastest computers in the world. It's updated every month. If you want to see what happens in HPC, that's definitely the site. It's called top500.org. And 2 years ago, it was only Chinese and Japanese here. Now, it's Americans. But from the 5th to the 20s, mostly are Europeans. So Europe is trying to catch up with HPC. We were dormant, as you have noticed, in a lot of domains, and now we're up. And so in the HPC now, from the 5th to 10th, there's a lot of European ones. So exascale, 1 times 10 to the power 18 floating point operations. So there is a European institution where we did this exascale project. It's called Euro HPC. They buy the clusters. They help to help the clusters. They help the countries from EU to buy the clusters. So Deucalion was paid by Euro HPC. Portugal had to put some part, especially normally, as in Portugal. I don't know how many foreigners are here, but I can criticize my country, right? You allow me. So Portugal is very good in CapEx, but not OpEx. So construction and funding money for making a cluster, fine. And afterwards we have to operate it. That's a little bit tough. So Deucalion is there, was paid by European Union. We have to help them guys to find some money to operating in order to let this live. But Deucalion is here. So it's the 219th and even the 18th green, because it's modern. You see the more green in terms of energy consumption. But Deucalion in Portugal is the 219th fastest supercomputer in the world, which for Portugal is quite good. And you see all this was in May, I don't know the other one. We have Lumi, that is in Finland, Leonardo, Mare Nostrum, it's in Barcelona. It was inside a church before. It was really cool to see a supercomputer inside a church. It was really nice. Carolina is in Czech Republic, Melonixa, I'm not sure where. And this one will be the Jupiter, will be the first exascale. I think Lumi is not, but Jupiter is in France, will be the first European exascale computer. It will be automatically in the top 5. And this is all money from our taxes, okay? European Union started to wake up. We have to have HPC. I don't speak about it here, but they have another things called AI factories, which for companies, they opening also calls for companies to use for free the clusters for AI calculations. So if you need big companies of universities applying for big supercomputing, this is democratized. I use these supercomputers and we are a company, okay? So Europe also realized that companies, SMEs, are the backbone of our economy. We apply for these clusters, we get CPU time, okay? So this project was done within Euro HPC, and they fund the projects called Inno4Scale. So it was innovations for the exascale, and this was the cascade funding. So there were these big institutions, Barcelona Supercomputer, HLRS in Stuttgart, and Scapus is a UK company, I think. And they gave money to these guys, and these guys fund projects that are disruptive. low TRL project. So imagine you have an idea, you apply, and they give you money to fulfill the idea. If it doesn't work, it's also fine. The research is like that. Sometimes it doesn't work. If it doesn't work, it's good that you publish it, contrary to maybe what people say, because nobody else is going to do that, right? You save some time for the others. So they funded a lot of disruptive ideas, and that's where we were funding. We were funded by InnoFoscale. New calls will be open for this. I'm in the loop, so if you need something, you can ask me. New calls will be open for any kind of disruptive ideas. So in this exaSIMPLE project, we partner Blue Oasis with Ineshktech, but more with in fact with MAC, with the Minho Advanced Computing Center. But Ineshktech thinks it owns MAC, but I don't know, politics, I don't care. But in fact, we used Deocalin, and André was helping us with Deocalin. So we partnered with the Portuguese companies and the institute where I worked before, of course. And so we had 3 Dutch, it is Polish, Dutch guys, Portuguese, Dutch, and so it's a lot of Dutch here, Dutch and Portuguese. Yeah. So this was the team that was working on exaSIMPLE. Because I'm in university, I have to show some equations. Okay? Today people were speaking about Navier-Stokes equations. I didn't see any equations in the slide. I said, how is it possible? Okay, so exaSIMPLE, the name is, we have to make the simple algorithm, that I will explain what it is, more or less, to be ready for exascale. Simple algorithm is an algorithm that uses in a lot of CFD codes, name it Fluent, Star CCM, OpenFOAM also has it, even if there was others. All the big CFD codes, incompressible CFD codes, they use simple or simple-based algorithms to do something that is the pressure-velocity coupling. So when you have, allow me to do this, I like to speak and I like to give classes, so allow me this. You have the Navier-Stokes equation, so you have the continuity equation. Let me, So this is continuity equation, and if this is for incompressible flow, you drop the density, and you don't have density here, and you don't have pressure in the continuity equation. And this is the momentum equation, and you have here a term for the pressure. But then, how do you compute the pressure? So this is decoupled, these equations, there's no pressure in that equation, so it's quite tough to compute the pressure when you don't have any relation between pressure and density. In compressibility, you have the gas or thermodynamic laws that connects the pressure with the density. But if it's incompressible, you don't have that, and there's a decouple. So you have to do pressure-velocity coupling. And the algorithm enters, simple algorithm, is to permit to do that. It's a trick to connect pressure with velocity. So when you're doing a CFD code, you solve continuity, momentum, any transport equations. If you do multi-phase, you have phase equations. And you have turbulence modeling. Also this morning, Ricardo showed turbulence modeling. This is an equation for a typical Kaum SST turbulence modeling. So you are solving all these equations in any CFD code. And then you have very complex geometries, okay? So you have a lot of equations and a lot of nonlinear terms. So all these things are together. So the algorithm of a general CFD code is that you have a time term, you have nonlinear terms. For instance, here you have 2 times the velocity, so it's a nonlinear term. And so if you're nonlinear, you linearize it, and you have a loop. So you have a time loop, and you have a spatial loop. So you have a time loop and a nonlinear loop. You can have operations with the grids. Well, this is like I'm talking about is OpenFOAM is like this. If you do CFD, this is very easy for you. Any code, the code of Hans is there. It's Riff3D also has some things like that, okay? So then you have a time loop and a nonlinear loop, and then you solve a lot of equations. And you solve the momentum equations, then you solve turbulence, multi-phase, and there's this simple here is in order to have an equation for the pressure. We need an equation for the pressure in incompressible flow. So simple does that. And simple is for an incompressible code, if you compute a car or a submarine, it's 90% of the CPU time is that stuff. So you have a lot of things, a lot of turbulence model, a lot of things that Ricardo said, it's it's for accuracy, but speed, if we improve a little bit what is the most expensive, then we can advance. Another thing for exascale is parallelization. Okay, so when you have big supercomputers, you are calculating parts of a ship in some cluster, in some node, another part in another node. At some time they have to communicate. This communication is a bottleneck. So there are two things to make any CFD code faster. Decrease, you can have more flops, so faster computers. Decrease the communication, so how to communicate as least as possible. Like some guy said last week in this project, he said, the best communication is no communication at all. And he was speaking to us, and I said, this doesn't apply to us, right? So in fact, for CPU, for computing, for CFD, the least communication is the best, okay? So the least you have to pass information between CPU and GPU, or between two CPUs, or between node to node with these InfiniBand cables, the best it is, and the faster it is. And you have to do that if you want to reach exascale in a CFD code. So we have to decrease, we have to do algorithm improvements. You can make this stuff faster. This simple has also a linear equation, AX equals to B. You can also make that faster. And of course, if it's a loop, a for or a do, the least iterations, the faster, right? So we try to get less loops, faster, simple, and once we have to compute a lot of equations, because these afterwards is discretized in an AX equals to B, and that solver has to be faster. So we try to tackle that in exaSIMPLE. How can we tackle the things that make a CFD code a bottleneck, and how can we start to work it towards exascale? It's a low TRL project. We have to disruptive stuff. Maybe it's not going to work, we thought, but let's try. And that's what EU pays to think out of the box. So we are tackling CFD incompressible solvers. You understood now why. All with simple. This is the typical example I speak about this algorithm. And we try to use ML methods to overcome the bottlenecks. So the pressure coupling, the approximations, I will speak about it, so the least iterations, and to minimize communication. Also, during the project, the war started and the energy problem started. They put also, try to prove also that your algorithm is also greener. So we don't have to do also faster, but we have also to do green. And you have heard that if you start to use a lot of AI, we're going to destroy the world. Because the energy, you heard that now that Apple and Google and all these companies are going to make only supercomputers, only to have even a nuclear power plant, possibly, to power their own clusters. So it will be that HPC, or the AI exascalers, so hyperscalers, will be the biggest energy consumption, or the energy burning in the world will be the data centers. So be careful. So energy is a problem, especially if you have seen 2 weeks ago or 3 weeks ago, if there's no energy, there's no AI. So, so what we have to achieve? Greener, faster, better. It's impossible, right? It's like prettier and smarter. It's impossible, or one or the other. I mean, so, but it's a EU project. We say yes, 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 yes. Let's try. So at the end, forget it. This has to reach to TRL3, and we are going to continue. So this was not finished work. We did some steps, and everything open source. Everything that we did here, you can use it. Okay. So. And we use our own CFD code, that is Refresco, that was my PhD, but we work very close to OpenFOAM guys, okay? So that algorithm that I presented before, it's now here represented in boxes. So the simple is this part, okay? The simple is to deduce a pressure correction. You have to assemble it, and you have to solve an equation. And the simple equation is this equation, okay? And because this has to be, it's funny, because I'm a CFD guy, and when I presented this to an AI person, he's like looking like he's reading Chinese. And when I saw, like 5 years ago, and these architectures, convolution networks, and and I thought that was also Chinese. So one of the stuff of this project was to combine people from the CFD world to speak with people from the AI world. They did not speak the same language. Okay? Solve an equation is not called solve an equation in the AI world. Inference, we call it completely different inference in the CFD world, you know? So this stuff was a good project to put people to talk together. So now I think the guys of AI know what is a simple equation or a pressure correction equation. So in fact it's to solve an equation for the pressure. These green terms are normally the terms that are considered, and like all engineers do, things that are difficult to calculate, we neglect it. We throw it away. And what we do? We do some more iterations, okay? So we want to decrease the iterations. So we said, now these terms here, let's consider, it's very difficult to calculate, okay? That's why we try. So, and that's one of the things that we did, is what we call level 2, is to consider, this in orange, is to consider these extra terms, the normal people disregard already from the 90s. Level 1 is to compute a normal simple AX equals to B equation, pure and simple, using machine learning, okay? We're not using mathematics solvers. We are all acquainted with GMRS, Krylov subspace solvers. We know all about that, but we wanted really to get rid of that stuff and try to use GPUs to solve AX equals to B, and to see what we could go ahead without any mathematic background. So that's level 1. And what we saw also papers doing is to abandon the completely simple and say, you know, black box, that I don't think it works, to put a lot of data, compute a lot of CFD cases. We have data, and we put in the black magic of machine learning, and we make a simple, let's call it ML-CFD. You know, just learning how to make this pressure velocity couple. The reviewer said, it's impossible, forget that. And we say, okay, we abandoned that part for this project. So now we have another project where we'll try that one. So we are only tackling the level 1, solving AX equals to B, with GPU and machine learning, and trying to estimate somehow the terms that we neglected from simple. Which machines we use? We use the Calnium, we use the cluster in Holland, we use our Iceland cluster, and we use in the Calnium 2 different hardwares. We use the x86 AMD that they have, but we also use ARM, and we also use afterwards the GPUs. That's not here, but it's in another slide. Why this? It's known, or people know, that ARM, the ones that we have in our mobile phones, are ARM-based, are much more efficient. Maybe less fast. They say also it's more scalable. So at the end, if you put a lot, maybe it's even faster than the other ones, but spends much less energy. So we wanted to see also, because of this green, that we had to show that algorithm was greener, if the algorithms were running better in ARM or in x86, Intel or AMD, doesn't matter too much, to be honest. Okay, so this is the Ocala that we use. And so everything we have done is in exaSIMPLE, it's in GitHub. So you can go into it. Good luck if you understand, okay? But if not, you can ask us. So we have Astrid and João Muralha, they did this stuff. So we did everything. How can we make an impact on this? We saw all the codes that are doing CFD, which libraries they use. All these codes that you use, the industrial codes, they use also open source libraries, right? If we could couple something with one of those libraries, the impact for the user will be faster, will be very close. So one of the best libraries in the world to solve matrix systems is PETSI. And so we hookup with PETSI using Python because it's prototyping. Normally we use C or Fortran or C++. But for prototyping we use Python. And so everything we did, it's PETSI compatible, meaning that if you have a solver that uses PETSI, you can also use everything that we have done. So it's PETSI, and of course we use all the traditional Python libraries for combining, in fact, PETSI and AI. So we combine CFD, solving the matrix, and AI in the same framework. So it's an exaSIMPLE.py. It's a code that you can go there. There's a lot of things in explaining that. And so this we already spoke about it. So this is what is the final deliverable. It's a framework where you can compute AX equals to B using SciPy, using PETSI, which is quite advanced, by the way. It's very difficult to beat it. It's from Argonne. I think it's Argonne Labs in America. So everybody is using that stuff. In all codes that you know, they use that stuff. You can have PETSI, you can have SciPy, and we have our own AI solvers, and that's very easy to compare and see when one is doing better than the other ones. So just for you to remember, we have this L1, that's the AX equals to B, and afterwards we have the L2, that is these extra terms, okay? So the L1, so what we tried. So what we try is that we have a flow problem. We have this flow problem creates a matrix, right? We discretize, we have a matrix. Then we put in our exaSIMPLE, and we have to try to solve the matrix. So one of the things that we add automatically is like literature review. How many people have done that? 2 papers in complete world. So we thought, we are crazy. We're never going to manage. Yes, we see at the end. But so people are not doing this. And we say, well, why is not? Yeah, we'll come to the conclusions on that. But one of the things was that we have to realize that, and I think somebody spoke today, with CFD problems, contrary to, for instance, what we do with HydroTwin, our dimensions change a lot. So you have a CFD calculation on a house, on a submarine, on a ship, or an airplane. You never have the same dimension, right? When you do AI for a computational vision, one of the things you have to do is to reduce the stuff for, 680 by 680 pixels or something. Dimensions have to be fixed. So one of the things that we had automatically to solve is which AI algorithm can we use that it's dimension independent and works for all kinds of problem sizes. Second one, memory. Python is very good for prototyping. You can forget, sorry, I'm speaking with guys here, very knowledgeable in Python. If you want to do a code that is, for instance, to run underwater, or to do a CFD code that does billions and billions of calculations, like the ones in the Ricardo, it's not in Python. You have to do it in a really assembled language, like C, C++. Even now there's other languages now. Rust, for instance, everybody's using. Even maybe you heard about Julia, that's another language that is getting also very much. Python is good for prototyping. That's what we used, okay? So, so one of the things that, I forgot why I was saying that. Yeah. So we needed to know which kind of architecture we're going to use. So the dimension, the fact that we had to use Python in prototyping, and so we tried to look into graphs, of course, because that we use also a lot for other places. So we tried to use GCNNs because of that, because of being dimension agnostic, because it's available everywhere in these frameworks. So we put our matrices in graphs. And in fact, a matrix from a CFD, it's sparse, okay? So you don't have a complete matrix, which again is quite different than normal AI problems, okay? So, and so we need also, we don't want a lot of, I know why it was, Python was the memory, exactly. So memory, Python is slow and is very bad with memory. If you do a comparison with C, you just go and Google, comparison between all languages. You see that a C code is 100 times faster than Python, and also maybe 10 times better than memory, okay? So one of the things that we automatically bump was into the memory when you have big dimensions. In CFD, big dimensions is millions, 80 millions, 100 millions of points. So it's a lot. If you use all these Python normally libraries, PyTorch, SciPy, forget it. You don't have memory in your code, in any of your machines. So we had to do some tricks in order to decrease the memory, also for the GCNNs. I mean, and the GCNN it's easy to understand, and we also, in order to decrease the memory, because we have a sparse matrix, we had to abandon the zeros. So it's an easy way of abandoning the zeros, because you make a graph, and you see all these terms and the connections between, and if there's a zero, there's nothing. So you lose all the zeros. So you decrease the memory. It's very good for dimensions, dimension agnostic. So we use GCNNs. We started with very simple architectures, and it didn't work. So we had to go to complex and the complex architectures. And we have a big report, and you see what we did. We're going to present the paper. So we did a lot of trials. We did a lot of hypertuning. And we achieved a working GCNN solver to solve AX equals to B to some precision that we wanted. Okay. So at the end, yes, we managed AX equals to B to solve using a machine learning, and we'll see what are the results. But it was much more complicated than we were expecting, and especially because of Python is the algorithm. It's an interpret language, so if it's faster than the other algorithm, we still didn't arrive to that stage, especially because of memory. It could not run in a normal Python code. So the second part, and I will present the results, was these green and these green terms. Oh, okay. The green and the orange terms. And so this is called, I'm sorry guys, this is called natural intelligence. It's not artificial intelligence. It's just that we try to, how can we compute these terms that everybody abandoned for the last 20 years? Why everybody abandoned the last 20 years? Because there was no memory enough, computers were not so fast, people all use simple, and now everybody uses AI, forgets also to study a little bit what it's inside. So what we try is to estimate these terms that are normally abandoned and only compute that. So in fact, the L2 developments, we are trying to estimate this, and to estimate this, you have to compute the inverse of a matrix Q, and this Q matrix, in fact, comes from the momentum equation. So that's why there's the coupling between the moment and the pressure. So we have to do the inverse of a matrix, and that's why we did L1. If you can do inverse AX equals to B, if we do that fast using AI, now we want to invert the Q also using AI. So the L1 had to be done first, then L2. So we do that, then we do this. So inverting a Q matrix in the old times, it's impossible. It takes a long time. So for the CPU, for the CFD code, that's why people were abandoning these terms. It's not doable. So we have to do something much faster to estimate these terms. And that's what we tried here. We tried to estimate this Q minus 1, so we invert the matrix, waiting for L1, there was the last one, but because the L1 was not advancing so fast, then we went to study papers from the 60s and from the 50s. Really, it was in paper still. And that was, yeah, paper. So, and that was, how can you approximate an inverse of the matrix? I didn't know this. So it's some nerdy guy from my team. He just said you can approximate a inverse of a matrix by a summation of inverses of much simpler matrices. Very simple matrices, which these ones are very fast to compute. And this is a Taylor expansion. So you maybe have to only use two terms of inverting very simple matrix to have an estimation of this one. So waiting for the L1, the full singing and dancing machine learning algorithm, we try to do something engineering approach. Just estimating the inverse by inverting simpler matrices to put it there to see what happened. And this was a big breakthrough compared with the L1. So, data. Aha, I knew that I was too slow. So, which kind of data we need? So we had data from several test cases, both for L1 and L2. We had simple canonical test cases. We had different grids, structured grids and structured grids. So this is a structured grid, simple, Cartesian. These are grids like more typical finite elements. So we have 2D, 3D. We have more than 10,000 matrix systems, both for the L1 and for the L2. where we also have to compute the flow. Okay? Disclaimer, it's not enough. We needed much more, and that's why the work is still going to continue. So for L1, this at the end, after so much work, we arrive to this architecture. So it's GCNNs with a lot of layers, and of course with the forward and the back propagation, and we have also, I cannot read, a regressor. So this is like, not me, the guys from AI team, trial and error, hypertuning, like based on knowledge, they manage this architecture that can, in some cases, so for all these 10,000 matrices, we took some to train, and we took and the others for the validation. And in some cases, it does really well. So you have here the predicted, the ground truth of a matrix, and these are the, so these are the comparison, and you see in some cases that there is really like, for an estimation of a matrix, A equals for the X, is really very good. In other cases, is really very bad. And that's like everything in AI world. It's like that. And so what we trying here was that we try to compute a lot of matrices from completely different flow cases. And we put it all together. That doesn't work. You change the Reynolds number, you change the boundary conditions, you change the geometry. It doesn't work. So what these work, and that's these cases, is that if you do train this solver for computing an airplane, if you come with another airplane with some small modifications, it does work. But try to put it in a car, it doesn't work. While if you solve the Navier-Stokes and you solve with the other solvers, it's much more general. So this AI, and I think the same with Ricardo was answering today, and I agree with him, these will work for specific applications. So if you train these for only ships or only submarines or only turbines, you make a solver only for turbines, for sure it works. And faster, better, and well, you train it in GPU and you run it in the CPU. And that's what we're going to pursue. If you want to have a solver that calculates everything, it does not work. That was our conclusion, and that's why we're going to do flow-specific solvers. For the L2, because it's more mathematics, we are not putting any AI, it's what artificial intelligence, that one is what I call natural intelligence, the mathematicians. So the exaSIMPLE is to compute these extra terms, the orange terms. And what you could see is that without these terms, you have these convergence lines, so all the iterations, and the other ones is the lines with the extra terms. So it's smoother. And this one is with the exaSIMPLE, is the number of these iterations that I show you. It needs always 2 iterations, and the other one needed like 25, 20. This is like 10 times faster. Okay? Not only that, but it's more robust. In any CFD code, you have something called relaxation terms. You have to play with them. If you use those extra terms, all the relaxation can be much faster. So the nonlinear part is also much faster. You arrive to the solution much faster. So here, with these examples, we got 20 times faster calculations just by estimating these extra terms. And how much cost these extra terms to compute? For 2 terms, not even 5% of overhead. For computing these terms of this k minus 1. And you see here again, for more complex cases, that it's still the same. The other one with the exact Q, so imagine you compute the exact, the other one with approximation with different terms, and you still get the same, maybe less, but for instance here with the exact term, which, I mean, 2 times faster, and then with the polynomial, maybe less. But what another thing is, because you have less iterations, less communication, this is for a real CFD code, these curves, these scaling curves, it's like also gets faster in terms of scalability. So this is the original one, and the green one, it's the scalability of the improved version. So less communication because you have less iterations, less non-linear iterations, less linear iterations, and more robust. So this one, we are waiting for inverting the Q1, Q minus 1 with AI, and then we see what we can do. but even by estimating the Q-1 with this very simple trick, everybody can do it. It's faster. Final slide is energy. So, and now does this work in different computers and different things? So we run all these calculations in a Dokarlin, and as suspected, you have here like different nodes, and this execution time and this energy, and you can see that in fact the ARM, well, we all knew that GPUs, you know this Terminator, what was the call of the company of the Terminator? Skynet. So Skynet is the NVIDIA, okay? NVIDIA is Skynet. So if we all start to use GPUs from NVIDIA, we will not have energy and resources in the world. It's the most inefficient CPU platform in terms of energy. Super energy consumption and a lot of heat, okay? So CPUs are much more efficient, and more than CPUs is the ARM technology. That's why we have all mobile phones. Otherwise, if you have a mobile phone from NVIDIA, well, we don't need heaters. We don't need heaters then at home. So you can see also here that in terms of execution time, of course, if you use GPUs together, because this exaSIMPLE can run in CPUs or GPUs, it doesn't matter. Of course, it gets faster. But you can see also the energy consumption there. Okay? So ARM, it's like, this is joules, but it's a tremendous, it's 6 times less energy. Okay? So watch out when you are doing AI using GPUs, because listen, remember me, this strange guy said that NVIDIA is Skynet. So, impact, final slide. Fully compatible with PETC. We did with Refresco, we would like to do together with OpenFOAM. We're talking with guys from Wiki, so Eric Rucha also to apply this to OpenFOAM. We would like a lot, Ricardo, we thank a lot the support of these guys. It's really cool. The cluster is very nice. I've never been there, to be honest, but very nice to use to use it. For Portugal, it was really, really breakthrough. We can do things that we could not imagine 4 or 5 years ago. We could not do all this work if we didn't have Dokarlin. I manage a project together with IST to continue this work, so I'm looking for a PhD and a postdoc. We will also make our own cluster in Fayal, so we will also try to work on this in the islands. And so, is the future this? You know what is this? Yeah. My future is this. This is the crater of Fayal. I prefer much more this stuff, right? This is really like this, it's really cool. So, what we would like to do together with some of you guys. We are very open to cooperation. We are really different. We're not afraid to work with competitors, anything. So we continue to work in all these 4 things. We will continue to work with Rift 3D, with Hans that's over there. We like to work with Indutiva, with like companies. We are also working with Air Center, that I think also you guys work for the Fayal. And in the AI, we continue to do stuff like, I don't know if this one works. You are spoiling my presentation. Why there's no internet? Doesn't matter. So, and well, this is the cool stuff we are doing. It's like also like in the AI world on identifying fishes. We have already real-time stuff, and so you can also go to our website and see Smart Fisher. It's streaming already, so you can. It's in a big aquarium where fishes, and it's already computing their size and weight and stuff like that, and sending via internet, and you have a dashboard. You can see this stuff. So that's another thing, all to do things underwater. And we are using a cheap NVIDIA sensor there. So, and I think that's my last slide, if I can. Yeah, so once you go to Azores, this is our new building. And we are doing stuff there with these people, and I don't say anything else. And so really want to make, I mean, these guys are funny in Portugal, in Azores. I did one, Azores is a very small place. So if you go to some place, I went to a bar, Peter's, you know, the famous bar in Azores, and I was talking to somebody, I said, wow, Azores could be the Silicon Valley. Well, they cited and they put it in a newspaper. And I was just in Peter's drinking gin tonic with the guy. So this is really in the newspaper. Empresa Blue Oasis quer tornar os Açores no Silicon Valley. I was drinking gins with the guy. So be very careful. So thank you very much for listening.
So Guilherme?
Yes.
I'm not trying to spoil your presentation, but on behalf of a person that was watching you through the live stream session, Paula is asking, does your derivable also detect when you have multiple solutions?
I didn't understand the first word, sorry.
Your derivable, that's the term, derivable.
I mean, you're speaking about, that's very...
I don't have also like a reference
question.
for the...
Can you say it again? Let's see.
Does your derivable also detect when you have multiple solutions? No further background that I can provide you.
If some of you understands the question, please tell me. Well, I mean, there's two things. First is the exaSIMPLE. The exaSIMPLE I don't think is connected with that. If it's the hydrotwin that is detecting stuff in the water, it does. So we can distinguish if it's a ship or if it's a dolphin. And if they are doing noise at the same time, we can distinguish because they are different patterns in the same picture. So if there's a dolphin speaking at the same time as a submarine, we can spread it and we can detect these two things, if that's the question. I don't know. When you do? Yeah. And if you have multiple solutions, you can store, right? Ah, yeah. That's this? Yeah. I don't know. So we tried that stuff with one term, two terms, more terms. And at the end, there's a, it's really problem dependent, to be honest. But most of the, it's even more interesting. That Taylor series where you do an inverse of a matrix by combination of versus of smaller matrices or easier matrices also has some coefficients. And those coefficients have to be trained. I forgot to tell you. So we can also train those coefficients. And again, it works good for specific kind of flows. I cannot put two terms with the coefficients working for all kinds of flows. So it's exactly the same. I mean, the extension, the validity, the application range of some AI is really very, for me, and for all things I've done, very case dependent. So yes, we can see yes.
Yeah, I hope you can answer to the question that was made online. Thank you.
More questions from the audience? I have a bit of a general question. Just wait a second for the online people to hear as well.
Oh, right, yes. Yeah, thanks for a super interesting talk. I think I just really drilled down on this thing of solving a linear system of equation with a graph neural network. It's kind of fascinating that you can, from what I saw just from the figure, the B are the node values, and then the actual edges, they are like right, the matrix. And so that you say that generalizes to all kinds of sizes of what kind of is that? When was this like discovered? And I guess I'm just like curious about the.
So the paper that we saw, the only paper that we saw that the guys did not advance a lot. I mean, we didn't invent that, so they did that. I can give you the paper, but they were solving matrices that were full matrices. And so we said, oh, if this works for full matrices, you can even abandon most of the zeros. It works even better for sparse matrices. So we used that that stuff that the guy did for sparse matrices. Because then, you can imagine, for sparse matrices, you only have to use the nodes and the edges for much less than for the complex matrix. So we thought for our case it was even better than for his full case. But his matrices were much easier to compute than ours, because the pressure correction matrix as something very bad, there is it's quiet hill condition. And it's like something called spectral radius very high. So it's a very tough problem, while some matrices are very easy to solve, right? So in this paper that we saw, the only one, his matrices were from finite elements or something more complex, full matrix, but much simpler properties, you know? And so his results were much better than ours. So that's why we used to say, oh, it's going to work. In our case, it only worked really case specific. We could not make it for all kinds of matrices working. But it's working. But if you train, only for some specific problems.
Okay, super cool, thanks.
Yeah. I can send you afterwards everything if you want. Yeah.
Maybe you have a quick question related to that. So, and when your approximation it's not really good, what you notice is that the simulation really diverges, or the effect is just like it will take longer, more iterations, and it will somehow compensate it at later steps?
For the solver, for the iterative solver using AI?
Yeah.
It stagnates.
It just like...
No, it doesn't diverge. It's just that we cannot... So what we have seen is that if you want to reach, for instance, you know, the residual, so the decrease, so the precision, let's say, of what you are achieving, if you want, for instance, 1 times 10 to the power minus 12, like machine accuracy, we cannot reach that. Okay. But in CFD, and I think there's some, you don't need that because you have a lot of non-linear loops, so you are never solving the right equation very often. So 1 minus 3 or 1 minus 4 will be already okay. But even that, only for very specific cases. What we're going to do in the next project is to put more features. So we will put some layers that put features of the matrix, like the condition number, you know, the sparsity pattern, the spectral radius. So we give more information to the neural network, because now it's only pure and simple a GCNN. And I think it will help. But I don't think we can make a solver that solves everything. We cannot do it.
Any other question before we move to the next talk, which, by the way, we might do immediately. I don't think we have time for a break now, right? Any other question?
I'm here. You can ask me afterwards.
Okay. So let's thank Guilherme again.
All right. Connect this one in, right? Not again. Okay, sure, thank you. And do I connect to Zoom or not? Okay. I send that to them.
Okay, everyone. So it's with great pleasure I introduce Professor Hans Bihs. He's a professor in the Department of Marine and Civil Engineering of the Norwegian University of Science and Technology. And he's perhaps best known of also being the main developer or leading the group that develops the simulator Reef 3D. It's one of the simulators actually we integrated also with the Indutiva platform. And so we'll hear about a hydrodynamic framework for offshore wind modeling, which is also related to the interests of quite a lot of people in the audience, especially people from the UpTwin project that care about wind modeling. So thank you so much for being here.
Okay. Yes. Thank you for the introduction, and thank you for the opportunity to be part of this. school. Yeah, I'm going to talk a bit about RIF3D. So I'm going to show a framework how to model waves and hydrodynamics. And I'm not so much focusing on machine learning, but I will show afterwards how this can connect to machine learning applications and how this can help. Okay. So I'm going to talk about RIF3D. So the motivation to start this model. You can see the motivation. I come from a civil engineering background, so started with the motivation harbor modeling, very traditional coastal engineering application, thinking about how the waves are approaching the harbor, interacting with the coastal structures. Coastal transportation, for us in Norway, a big topic. A lot of roads and bridges are very close to the coast. But then, of course, there's a lot of offshore applications, offshore energy. We have the traditional offshore oil and gas, but now, of course, offshore wind energy, there's a lot of focus on. Aquaculture, and one of the projects we have been also involved was the E39, it's a floating bridge, something that still has to be built. So these kind of applications, we have structures in the sea at the coast, and we need to know how the sea is going to interact with those structures, what are the forces, what is the loading on those structures, and how do we have to design these kind of structures to be stable. So we have RIF3D, open source hydrodynamics. This is developed at NTNU by my team, and our focus is really on multi-physics for hydraulic, coastal, and offshore engineering. We want to have all those applications that are relevant in those fields. And at the same time, we want to have a multi-scale framework. We want to be able to look in the near field of the structure, but we also want to be able to bring the waves close to the structure. So that means we have to bridge length scales several kilometers down to maybe centimeter scale. Some background. So yeah, typical North Sea coast looks, for me at least, like this. This is the northern part of Germany, southern part of Denmark. This is on the western side is the Wadden Sea, and you can see this area is quite shallow water, maybe 10, 20, 30 meters maximum. It's tide driven. There's a lot of sediment transport going on. And yeah, a lot of the wave models around the world are built for these kind of conditions. Then if you go to Norway, Norway has a quite unique coastline. This is a very extreme example, but I think it shows the situation quite well, how it looks like in Norway, most of the places. So there's a lot of deep water areas with very rapid water depth variations coming from the offshore towards the coast. You can see on this image, this is Andenes with this harbor, very exposed harbor with a very strong breakwaters, fortified against incoming waves. There's also strong diffraction because we have a very irregular coastline and a lot of small islands. So the waves, they interact with the islands, with the coastline before they reach the point of interest. So a lot of, we call it wave transformation is occurring. You can see also here this harbor just about 20 kilometers offshore from the coast. We reach more than 3,000 meter water depth. This is a very special case, but so the conditions in Norway are very extreme in this case. So when you look at the commonly used wave models, there are some limitations there. Spectral wave models, these are the more global wave models like a WAM or WaveWatch, but also in the coastal scale, you may be familiar with SWAN. But when we come really to these kind of conditions, a lot of diffraction, spectral wave models have limitations. They're really great for a lot of things, but for these applications, it is a limitation. Then we have shallow water wave models that resolve the waves, how they are propagating towards the coast, but they are limited by design almost because they're based on the shallow water equations. They are limited by the water depth, so there's a limit there. Then there are other simplified models, which are 2D models, like, for example, a mild slope model that is limited then by the depth gradients. This is the motivation why we started to build wave models. We wanted to address the situation in Norway. So really the first wave model that helped us out here is called RE3D FNPF. FNPF stands for fully nonlinear potential flow. The great thing about potential flow equations is that they are not limited by depth. The waves are propagated without any artificial diffusion. Yeah, what we really did here, I mean, potential flow models have been used for many decades already, but what we have done here is bring them into the context of a coastal wave modeling. So we also have a coastline, we have bed changes, and this is all possible to model with the FNPF model. So the key here is it's possible to model waves from the deep water towards the shallow region, including bathymetry effects. Yeah, one example here is this animation of Bjørnafjord. And you can see it's 45 by 35 kilometers, so it's a really large scale area we can model. With this kind of model, we have the swell, so these are the offshore waves coming in, and you can see then how the waves will interact with this part of the Norwegian coast. You get all the diffraction and also refraction. Refraction means that the wave fronts, they want to be parallel to the contour line of the bed. So then that leads to also turning of wave fronts. And you can see this happening in the simulation. We are solving here the Laplace equation for the velocity potential. It's a three-dimensional model in that sense, because we need to know the velocity potential in 3 dimensions. And we use something called a sigma coordinate grid, which will follow the bed topography, and it will also follow the moving free surface. Then the great thing about the potential flow equation is that the crucial boundary conditions, they are only 2-dimensional, so they're quite efficient in that sense. What we did, we added a so-called coastline algorithm because yeah, can be quite complex bathymetry. We didn't want to have a mesh that has to be adapted to the coastline. What we just have a Cartesian background mesh, identify the coastline, and add an additional beach region around the coastline. The potential flow solver has some difficulties simulating the run-up and run-down of waves on the beach. So we are just mimicking this effect of this dissipative process by adding the relaxation zones around the coastline. So this model is really good at giving back the effect from the coastline. It's not so good at really looking into this wash zone area where the breaking is occurring. But it's still good for a lot of relevant applications. For a potential flow model, what it needs to be able to do is survive breaking waves. So the waves, as you can see here in those images, means the waves will break, and then all of a sudden we have multiple free surface points in the horizontal plane. And this is something these kind of models are not built for. So when breaking is detected, breaking wave model is activated and is included in the governing equations. Yeah, one of the applications for this kind of model is in the Norwegian offshore industry. This is an aquaculture site that was in the planning, which is located behind an island which is called Flatøya, means flat island. You can see this is the Flatøya here, and this red square is the aquaculture site. And on the way towards the site, the waves experience a lot of transformation, a lot of diffraction. So as part of building such an aquaculture site, so these are cages moored to the seafloor, and this is where the fish are being grown, typically salmon. And it's very crucial that these cages are designed to withstand the waves to prevent the fish to escape from this location. you can see the animation here, incoming waves from the offshore side. So we have turned the domain a bit, so the main wave direction is aligning with the boundaries, so we avoid reflections from the side. And looks a bit chaotic there on the way towards this flat island where the aquaculture cages are located, but this is all due to refraction because we have the huge variation of the seafloor almost reaching the surface. So this is now a domain 14 by 3 kilometers, and so typical for offshore design, we need to have 3 hours of wave conditions. This is for one instance. Typical, you would have many instances, hundreds or thousands of instances. But it's always 3 hours because that would equate to 1,000 offshore waves. And from this, you then can derive your wave forces, your statistics that is needed to design the structures. So what we did, we compared the results from the phase resolving model, and I think this is a good spot to explain the difference between a phase averaged wave model and a phase resolving. On the left-hand side, you can see a phase averaged wave model. This is SWAN, a spectral wave model. That means it's not calculating really the wave trough or the wave crest propagating, but what it does is it's calculating the wave energy, how it's being transported and transformed by bathymetry. But some of the physics is just not there, and in that sense, you can see the phase resolved wave model. The wave crests are really propagating, interacting with its surrounding, and such a model is much better equipped to take care of the wave diffraction. This is how the wave will interact with obstacles. And diffraction effects leads to the following phenomenon. Intuitively, behind an island, you would assume is a sheltered area. But because of diffraction and also refraction, the waves will actually move around the island. And so now if you have this kind of island, you don't only have one wave coming in, but you have 2 waves coming in. So this typical circular island scenario, the waves are higher on the lee side than on the front side. So you should never, for example, have your ship behind the island because of this effect. So here, with the spectral wave model, we are missing the diffraction effect, and that would give much lower waves behind the island. And now with the phase resolved wave model, we capture all the physics, so it's a much more accurate estimation of what is happening in this region. So in this sense, this kind of model brings a much better detail, quite new capabilities for the large-scale wave modeling from deep to shallow water regions. So when we then compare for 50 wave gauges behind the island at the locations of the individual cages, so what you can see is with the spectral wave model, the waves are underestimated around 30 to 50%. So that's quite a significant underestimation. This then directly correlates to the wave loads that those structures will experience. Coming back a bit to the offshore wind theme. So this here, you can see the image is the deep water wave flume of SINTEF Ocean Research Institute in Trondheim. It's an institution that we as NTNU collaborate with a lot. So in this case, what we have done together with researchers from SINTEF Ocean, adapted the FMPF model to those wave flumes. That means we have included the kinematics of their wave maker. So you can see the experimental wave maker. It's a so-called 2-flap wave maker. It's a 10-meter deep wave flume. I think then the top 2 or 3 meters is equipped with a double-flap wave maker to create waves. And the kinematics of the wave maker we have included in the numerical model. We are then reading in the motion of the wave maker and recreate the exact same waves as the experiment in the numerical model. So then there's this large Norwegian project on offshore wind structures. It's called exaSIMPLE. And for this, there were many tests for loadings on monopiles. You can see the sketch of this monopile with the load cells. So here, the information we have is we have the motion of the wave maker, we have the measurement of the forces on the monopile, and in different locations in the wave flume, we have the measurements for the free surface elevation. And the idea here is to test for more severe steady states, nonlinear waves, steep waves. And what we have built into the numerical model, instead of resolving the structure and the vicinity of the structure, we use something called the Arley-Morrison force equation. So based on the hydrodynamics, we can semi-empirically correlate the wave field and the underlying kinematics to the wave forces. I'm going to show a bit more about how this would look like. So you can see on the left-hand side, we have the wave tank without any structure inside, but we have the information of the flow velocity underneath of the wave. So you can see here quite steep waves, and that means steep waves. Then we have this really large magnification of velocities around the wave crest, leading also to quite large forces. So then we can compare, because we have phase-accurate waves, we are recreating the exact same waves as in the experiment, even though we have here irregular waves. We can then compare the free surface elevation for different wave gauges. That's the top figure. We can then compare against the measured forces on the cylinder, and also at the global moments, which is also an important parameter, compare with the experimental measurements. And so this is a very efficient way, because today many models still use wave theory to quickly estimate wave forces. And then what's missing from this approach is the physics, the wave interaction. A lot of the nonlinear effects are missing. So with a numerical model that reproduces complete nonlinearities, it's possible to move much closer to the real world physics. We are currently involved in a research project called B-Waves, which is based around Equinor's Empire Wind project, which was in the news, at least in Norway, quite a lot recently. But luckily, the project is now continuing. It's a large offshore wind field in the vicinity of Long Island, New York. And so this was one of the first times that or if not the first time, that for the design loads, the whole pre-design was done with the FMPF model by Ocean. All the wave loads, that means thousands of wave condition scenarios, wave load scenarios, based on experiments at Ocean. This is a very difficult location because there's a combination of the swell incoming, so the waves from the Atlantic Ocean, but then also here what needs to be taken in consideration is the hurricane. So we have in addition the wind forcing even steeper waves, so a lot of steep waves for these scenarios. And with this FMPF model, it's really possible to consider the nonlinearity of the waves. But I mentioned already there are some simplifications to this FMPF model. It's really good at propagating waves. It's really good, use it as a wave force estimation tool. But when it comes to coastal processes, there are some limitations. Well, it cannot handle the run up and run down at coasts. And since it's a potential flow model, it cannot consider a rotational flow. It cannot consider viscous flow. So if we want to look at real world coastal processes, such as, for example, wave current interaction, that means we have turbulence, turbulent flow, wind forcing, for example, in addition to the propagating waves, but also other physics like sediment transport. The potential flow model is limited. So what we did is we built a new wave model, NHflow, which has wave features similar to the potential flow model, but it's built around the Euler or Navier-Stokes equations. So it can include all those effects. So here we can see an example. This is Arizona, yes. But just for fun, we added some wind forcing on the surface. But what you can also then do, you can look at a cross-section and look at sediment being eroded. You can see due to the run-up and run-down there, sediment transport occurring. So this is much more capable for multi-physics simulation, but still at a large scale, still very efficient. I'm going to show a bit more about this model. I think it's very interesting and very exciting for us. So this is the matrix of Re3D, the different models we have. I'm not showing the S-flow model. It's a shallow water equation model. We use it a lot for shallow water waves or coastal regions or rivers. FMPF you saw now a lot, and possible applications for offshore wind design. I'm going to show in the end a bit about CFD. This is the high resolution computational fluid dynamics solver for two-phase flow. CFD delivers all the different aspects. Dispersion, that means possible to model deep water waves. Wetting and drying, that's the run up and run down on the beach. Viscous effects are there, that means we can model turbulence. Breaking wave is possible, fully resolved with a two-phase flow model. It's three-dimensional, but in the end, of course, it's very expensive. And now this new NH flow model finds the sweet spot between the very efficient FMPF model, which can run from deep to shallow, is very fast, but has limitations when it comes to wetting and drying and turbulent flow. So NH flow ticks all the boxes, while at the same time being very efficient. So this is the model I'm going to show a bit more about now. It's using a very similar, if not the same, mesh as the FMPF model. It's a three-dimensional mesh that's, again, a sigma-coded mesh. But we are now solving different equations. We solve now either Euler, that means Navier-Stokes equations without viscous terms, without turbulent effect, or the full Navier-Stokes equations. Yeah, I show on the next slide the set of equations. What we're doing here, we are using a Goodenough type scheme, so we are following the concept of a shallow water conservative numerical treatment, and that has, for the user, the interesting effect that it becomes conservative, but also shock absorbing, because we use an HLL Riemann solver with a high order reconstruction. And I will show how this is really interesting and important when using this kind of model. Important for this, or for the performance of NH flow, when it comes to dispersion, the ability to model waves in deep water, is the pressure solver, because now we need to solve the non-hydrostatic pressure. That helps us to maintain good dispersion properties. And here we use the pressure correction method, which was really a big difference for us. For the Poisson solver, you said PETSI. I think there's one better. It's Hyper. Yeah, Hyper is also partially included in PETSI, but those guys are really focused on just on the linear solvers. And what we can use with our mesh, we can use PFMG, that's a geometric multi-grid solver. Together, that's the that's the preconditioner, and then as the solver itself, it's the BCG stub, so it's also conjugated similar to GMRES solver. Everything in Re3D is domain decomposed for parallel computing. I'm going to show a bit about the performance later. So here is a small example. There are two aspects you can see now here. Wetting and drying, but also the shock absorbing properties. This is a conical island. I'm going to start the simulation in a second. Just pumping in some waves, deep waves, and how they will interact with this island. This is just 150 by 150 by 3 cells, so it's not a lot of cells, runs really fast. You can see the waves. I just let them reflect on the wall, but you can see the run-up and run-down on this conical island. A lot of reflections, and there would be breaking waves. This kind of model will not give you the overturning crest, but it will mimic the kinematics, so the energy dissipation through the breaking process is included. But because it's shock absorbing, it doesn't need any additional treatment for those conditions, so it's very stable. I want to show some validation for this case. After my PhD, I started to work at SINTEF Coast and Harbor Laboratory. So one of the projects they were doing at that time was Meerhaven Harbor. This is the most northern harbor the Hurtigruten goes to. So this is passing the Nordkap even. And this is a project around 2008, 2010. There were waves entering the harbor. Not a problem for the larger ship, but for the smaller fishing vessels was a huge problem. So you can see already on the right-hand side how it looks like today in Google Earth, which includes the solution to the project, adding 2 breakwaters. But it's a natural harbor. You can see this on the image there. Should shelter against waves. But for some wave directions, it was noticed that the waves became really high. So how does it look like? So in a SynthF Coastal Harbor laboratory, at that time, these kind of numerical models, which I'm showing today, were not available. So everything was done in the laboratory. So you can see the image from the experiments in the middle. You can see the harbor, and you can see these white sticks. These are the wave gauges. There are 9 wave gauges in total. 1 is located outside the harbor and 8 further inside the harbor. So before we go to the real or for the comparison, I just want to show with regular waves the kind of wave features for this condition and what is happening here. So you can see due to the diffraction around this part here and refraction, the waves are really turning towards the entry of the harbor, and due to further diffraction around this part here and refraction, the waves are really turning into the harbor. So they're turning multiple times, and in the end, waves are actually entering the harbor. And so it's really important to either capture this in an experiment or in a numerical model. So what we have is we have the measurements from these experiments. Again, these measurements, they were run each of them for 3 hours. And what you then do is, instead of looking at individual gauges and look at their elevation, it is post-processed into significant wave heights. So this is basically the average of the 3rd highest waves at each of the wave gauges. And so this is something we look at a lot in coastal and offshore engineering. So HS, significant wave height, there are 2 cases. One with a slightly lower wave height, 3.5 meters, and a shorter peak period. And what you can see is the wave maker in this case was a bit older, so it was able to do irregular waves, but not multi-directional. So it's irregular, but so-called long-crested waves. These are just some snapshots. And then you can compare the significant wave height for wave gauge 1, which was located outside the harbor, and look at the different wave gauges inside the harbor. You can see this kind of model can reproduce really all the physics quite well, similar to what the experiment gave us. So that's very useful, good validation case for the numerical model. Yeah, coming back to Ericeira once more. We had this project together with Blue Oasis and Guilherme. So we are continuing to use this case for several things. So this is actually a new simulation we did for a recent publication or submission of a manuscript because we wanted to have a large domain, and luckily we had the topography here from Ericeira, so we made this a bit longer than what we did previously. We made it now almost 9 kilometers by 18 kilometers to get to 50 million cells for this energy flow model, and we're running the waves. What we wanted to do here, and the project, we were interested in the wave conditions for the different beaches for the surfing, but what we want to look at here is at the HPC scaling. So we are running this on a supercomputer, and what we were interested in looking at how does it perform for the different core counts. So on the next slide you can see the scaling for the supercomputer that we use mostly. It's Sigma 2's. That's the Norwegian supercomputer infrastructure, and the supercomputer is called Betsy. When it came out in 2020, it was on place 61. Now it has been relegated a bit, but it's still in the top 500, so it's still there. And yeah, it has a lot of CPU cores, over 170,000. The range at which we use it typically is 1,024, maybe up to 2,048. So for this here, we ran at from basically one node up to almost 2,500 cores, and look at the scaling for this, which looks really positive. We see that it's exceeding the linear scaling. What we think what could be the reason for this is that at some point some communication gets activated between the different nodes. I don't know, but
depends on the cache. You have a lot of possibility to use more than of the cache than RAM, and then it gets faster.
Yeah.
It's quite common. But then it should decrease.
Yeah, but okay, we are using here 50 million cells. So at some point it has to decrease, but for this, yeah. Yeah, still pretty okay. Yeah, we probably should continue. But and then what we also looked at, because the layer number in vertical direction, that's important for dispersion. So when we add more layers, it should be able to model waves in deeper waters. And here also, in that sense, the positive news is that the scaling here is also linear. So we add vertical layers, and that just relates to more time in linear fashion. Yeah, I want to show one more, going back a bit to physics, what you can do with this kind of model. One of the simulations we have done was from Nazaré, also from Portugal, which is known for the largest waves in the world, I would say. And the reason why those waves are occurring there is the submarine canyon moving towards this cliff. You can see on the Google Earth image, I think the pointer probably works, so I can use this. Yeah, I think, yeah, so you can see this is the cliff with the lighthouse, and in front of the lighthouse these large plunging breaking waves occur. And yeah, this is the lighthouse, the breaking wave up here, and you can see towards this cliff there's this submarine canyon moving towards the coastline. So you can see it a bit better here. The cliff is here, and this is the submarine canyon. And in order to understand why these waves are so high just in this location, and understanding the effect of the submarine canyon, we also ran this NHFlow model. And now this is a domain, almost 60 million cells, 3.3 kilometers by 11 by 17 kilometers. And this is the cell count. We used 8 vertical cells. So what we did is we prescribed irregular waves, swell wave conditions with HS of 8 meters. And then you can see at this cliff, which is located here, the waves, and I will zoom in a bit more, the waves are really higher than in the surrounding. And this is because we have waves propagating towards this spot, but at the same time, waves from this area, due to refraction and shoaling, they are meeting the other waves, the incoming waves. So you get kind of this wave focusing due to the submarine canyon, and that releases then the wave energy into the breaking waves. So with this kind of model, it's really possible to. Yeah, we didn't pursue this any further. We are now talking to Norwegian Meteorological Institute. They are measuring at this spot, and they were looking for a numerical model, and that's something where we will contribute with our simulations. We just picked this wave heights, but just to show the effect. Probably you need to have a bit higher incoming waves to recreate the 30-meter waves. Yeah. Okay, then I have until 4:15, you said? Yeah, okay, so that's some time. Since we have now in NHFlow Navier-Stokes or Euler equations, we can do more modifications to the equation than in a potential flow. In potential flow, when we bring in extra physics like wind or structures, we need to modify the velocity potential, and the relationship between velocity and potential is to gradients. So modifying the gradients can be always a bit tricky. But since here we have Euler equations, if we want to include structures, we can relatively straightforward, as we also do in our CFD solvers, we can include a forcing term. and bring in the effect of structures into the flow or wave field without adapting the mesh. So this is a method called immersed boundary. So we can bring in quite complex geometry into energy flow now without really changing the underlying mesh, and that makes it quite straightforward. I want to show some of the possible consequence or possibilities out of this. So what it means for now a cylinder, if you really place it into the domain, instead of what we did for the potential flow where we were just correlating the wave force to the kinematics, now we can really place a cylinder into the domain. We have a non-hydrostatic pressure, so it's possible to integrate the pressure over the surface of the structure and then get the forces that act on that structure. So here's an experimental case where we compared against the measurements for free surface elevation and also the inline force, the wave force in wave direction. So now it's possible to relatively efficiently calculate the wave forces. Cases like this, if you go into the literature or industry, typically if you want to resolve the structures, arbitrary structure geometries in waves, you have to go to CFD. So now the intriguing possibility here to use energy flow, much more efficient, but still be able to resolve structures. Yeah, when we can continue the idea here a bit. We have now a floating structure. We can calculate with a direct forcing method the force on the structure. This is OC5, an industry benchmark, semi-submersible, floating offshore wind structure. The tests have been done at Marin in the Netherlands. And we can then, with the hydrodynamic forces, we can solve the rigid body equations, so the floating motions. Then, with the energy flow solver, the mesh is the sigma coordinate mesh. We can immerse the floating offshore wind structure. There are mooring models available in V3D. We also offer coupling to other available mooring models, like for example Murad, and then it's possible to calculate the motions of a floating offshore wind structure. Yeah, we compared this preliminarily to experimental data, and so we can quite close to heave, pitch, and surge motions for this case, something that's still ongoing work. We have also built on another, through a master thesis, we have built a connection to OpenFast. So you can use energy flow as a wave generation to OpenFast. Because in OpenFast you have first or second order wave theories. Now you can combine with realistic nonlinear waves from V3D and then look at the motions. That's another possibility available now when it comes to offshore wind. But I also want to show this case here. So go back a bit to harbor modeling. This is harbor in Norway again. This is Sirdevåg. That would be, as it stands there, a typical harbor study, breakwater study, for example. There's a large breakwater providing waves to enter, or harbor tranquility study. But in energy flow now, with the ability to have floating structures, we can add, for example, in the same domain, we can add a floating ship. Now we have a 6 degree of freedom motion simulation. We have realistic bathymetry. We have a realistic sea state. We have relatively large length scales. So if you think about the 6 degree freedom simulation in CFD, that's typically vicinity of a structure or ship. Now you can have full context and still nonlinear wave and floating interaction. Of course, this is not a suitable tool if you're interested in near field viscous effects, boundary layer resolving. This is not what this model will provide, but when it comes to nonlinear waves, this is a possibility. You can also now replace a ship. You can put in a floating offshore wind turbine in real world bathymetry and sea states. You can have a whole field of offshore wind turbines, and all can be done with a single simulation. Yeah, I want to, as a final part, just also outline the CFD model. So when we have done all the large-scale simulation, it's possible to couple to a high-resolution CFD model. And in contrast to the other two wave models which you saw, CFD model can resolve two-phase flows. So you get really fully resolved breaking wave, including the jet and the whole three-dimensional wave, water-air interaction. So that's really the key feature here. And in addition, yeah, it's high resolution. You get all turbulent effects. You can run LES simulations. So this is the suitable tool for the near-field simulation. For offshore wind, we have done a lot of these kind of simulations. This was a research project together with the university in Stavanger. We performed experiments in the large wave flume in Hanover at the Coastal Research Center there. That was sponsored through Hydrolab. So this is a jacket structure in a really large scale, 1 to 8. Was placed into the large wave flume and then tested for breaking waves. In the CFD model, it would look like this. We see here the free surface. Now the first wave should not fully break, but then the second wave has a trough to break into, and you can see now we get the full breaking wave kinematics. There's absorbing beach on the end, and now what is happening? The wave first hits the front of the jacket and then the back of the jacket, and this is why you get a force signal with two peaks, first the front and then the back interaction. This is compared against the measurements from the WaveSlam experiments. And you saw already some floating simulations, so I'm not going into detail here. Of course, in the CFD model, you can also use floating, can do a bit more complex things like, I mean, we can do the floating offshore wind, but also add, for example, nets, either static or deformable nets, multiple mooring lines, and look at response, for example, at aquaculture structures, wave loads, etc. It's possible to connect to multiple extensions when it comes, for example, to sediment transport is built in. The floating structures we looked at a couple of times now. We have non-Newtonian rheology. Look at, for example, debris flow or granular flow. Porous structures such as, for example, breakwaters, vegetation, environmental modeling is a big topic, or stratified flow, saltwater, freshwater interaction is also possible in the CFD model. Yeah, just looking at the sediment transport in the CFD model, this is a seawall scour, for example. So we have now a mobile bed. We look at the bed shear stress connected to bed load and suspended load transport formulas. So it's possible then to calculate the response there, transport of sediment, and resulting scour. When it comes to offshore wind, sediment transport becomes relevant. As you can see on the bottom left side here, becomes relevant for local scour calculation. All the bottom fixed offshore wind structures are in contact with the seabed, sandy bed, and so there's a huge bed shear stress amplification leading to erosion and local scour. That is of high relevance when it comes to structure stability and scour protection purposes. I'm just wrapping up now with the last slide. So we have looked at all the different models, and what we have built in the recent years is something we call NORA-SARA. NORA is the name of the hindcast databases in Norway when it comes to mid-ocean conditions, and also with collaboration of the Norwegian Meteorological Institute. We have built the system to go from the hindcast databases, NORA 3, NORA 10. The NORA is the interface that either go to SWAN or go to Re3D directly as an input, or you go directly from NORA to Re3D, that's a possibility, and then move into the CFD model for the near field simulations. I think I stop here, so it's also possible to have some questions afterwards. Thank you very much for your attention.
Wow, I come from the machine learning community, but I find this much more impressive. So questions from the audience?
Thank you for the presentation. Can I just ask about this MetOcean? Is this you get your boundary conditions for the simulations from this?
Yeah.
It's a reanalysis or a mesoscale model. What is it?
Yeah, this is it's both. It's databases, but also ongoing modeling, like WaveWatch 3 models. So you have global models you can hook into to find your MetOcean conditions.
Okay, thank you.
And this system, it's about downscaling. So you have the global scale, you need to downscale it to your locations. That's the key. And especially if you then go into locations inside the fjord, there's a lot of transformation of waves occurring. In addition to that, there are also local wind waves. So you need to also consider local wind effects on the wave fields.
Okay, so I'll be reading a question from the live streaming session as well. So Lawrence asks, do you know if any of these models can be used to map the coastal flood due to overtopping in an urbanized area?
Yeah, I think that's definitely possible. So I know that the shallow water equation model, which I didn't show in detail here in this context, but that has been used for commercial applications for urban flooding. And NHFlow should be also able to handle that well.
Hans, hello. So I'm waiting for the NHFlow, as you. So what's the status? Can you advise us to use already for industrial projects or with some caution still?
Yeah, so NHFlow is fully validated for all wave application problems. And we are currently validating the structures. Some initial validation happened. Then wave current interaction is something we are working on right now.
That's what I'm interested. So you know that we have these models of RIF3D for the Azores. Yes. So after I decided that we did together, we are now doing models for the complete Azores. But of course, there the currents are very high, and also we need that. So we are very much interested in this, and of course we will have also validation data from our sensors. So don't forget if you need data for that. Another question related with that is that, you know, there's other codes that do these that we are using that we want maybe to abandon to use this. Can you include more transport equations on an HFlow, for instance, to transport, imagine, pollution, biological mass, sediments, dispersion, you know, when you're doing dredging? Is there something that we as a normal user can do that easily, or you have to build something for that?
Yeah, so sediment transport is there, I would say, as prototype. We are having, we have 3 PhD students starting right now, working in these directions. So then there will be more results very soon. And validated model.
Yeah. Have you compared with MOID and Delft3D, which is an NHFlow kind of tools that everybody is using in the world?
Yeah, MOID, I think it's more like an ocean model, I would say, right?
Yeah, but Delft3D is also...
Yeah, Delft3D is definitely one of the standard models for coastal modeling when
it
comes to tide driven, especially, I would say. Sediment transport, we have not compared against yet.
Okay.
But something we may do in the future.
Because it's an old code, so it scales like shit. So, sorry, pardon my French. But so in terms of parallelization, you can easily beat them in terms of performance. But it's a code that a lot of people use, so you have to prove that it does exactly as good as the others.
Very well
known
and validated.
Yeah.
So, that's of course a very high value in this kind of model. It's really a proven model, and it's very hard to replicate that. I think NHFlow has the potential there when it comes to sediment transport, because it also includes the free surface effects, waves.
Yeah.
So you can have current and wave So it's possible to
Yeah.
look at the physics combined. That's something we would like to do.
Yeah, I think in Azores we can do something together there. Yeah.
Hello, good afternoon. I should let everyone know that I'm not a scientist. And so, sorry if my questions don't make much sense. But first question, regarding that Flatoya project, you've shown quite big differences between the two modeling efforts. Okay, they are different, but which one is more accurate? Do you have an idea? Do you have local measurements that...
Yeah, for these conditions, there are no measurements because to get basically the design significant wave heights, you need to measure for a long time.
Yep.
We have other experimental comparisons. We have done this, for example, for this Meerhaven case, for this harbor. So it looks really like that. When it comes to diffraction, spectral wave models are limited.
Okay. Do you happen to know if that project was built?
Yes.
It was?
This was a master thesis, so we didn't do the design or anything.
Okay.
We approach it from a research perspective.
Okay. I represent the other side. I represent the enterprise side of the things, and I'm here willing to absorb what you guys can provide to the, let's say, investment world. And I had another question. So I noticed in that you guys model very defined scenarios, specific conditions, specific time, specific direction. The real world is a statistical, right? Help me. Distributions, all directions, many speeds, blah blah blah.
Yeah.
So, are you guys able to replicate these simulations thousands of times in order for us, from a, let's say, structural point of view, pick the worst case scenario from all directions, all wind speeds, all currents, and come up with a structure that, let's say, can withstand 50-year, 100-year high winds or currents or waves?
Yeah, for example, on the mid-ocean scale, there's multi-directional information which we are using. So we have, for example, the most important wave directions. We can see that from the directional spectrum. We have wind directions, so that's something that's always being tested. So let's say for engineering purposes, we would test all the directions, all the wind wave combinations. So then it comes down to many instances of the simulations, and from this you can then derive basically governing conditions.
Just to add something on that question, is that's something where I was also waiting for the FNPF and NHFlow, these acronyms, you know, because these are so much faster than the normal CFD that we also do, that it permits to do all these thousands of
Scenarios and long-term calculations that with pure CFD are not possible.
Can you define for someone that is...
What is fast? Yeah, well, I think he can, but what is a fast calculation from NHFlow? For instance, this one in the Ericeira. Can you do it real time?
Yeah, if you use enough computers.
Yeah. But what is enough cores?
I would say, but yeah, I mean, these are more the extreme scenarios, right? But if you say, take a Meerhaven harbor, you can do real time on the laptop. Yeah. And then the idea is, of course, that's not the one, but you need to have many different conditions. So, like I said, Empire Wind was thousands of conditions. Yes, that takes time, but it's possible. It's definitely more possible than to run thousands of conditions in a waveform. So it's much more limited. Yeah, but I mean that's really the key. So
for free.
So maybe a quick question here. So Guilherme showed before a hybrid algorithm between machine learning and CFD. So if you could speculate in that direction on the kind of research you do, where would you see a big opportunity for ML to contribute?
Yeah, so I skipped a bit on this in the end. I thought it went a bit too long, but if you, well, something we have done, we have expanded the NORA-SARA, which includes basically the downscale from mid-ocean scale down to the near field. We added machine learning in that sense, so what it can help for machine learning can help for operational conditions, so it can train the model and then without rerunning the simulations under operational conditions. I think that's where it becomes very interesting.
Mostly what we also would like to do for the digital twinning is surrogate model. So it's like you're teaching an algorithm that is much faster, the inference is much faster than the training, and then you can run millions of scenarios that you train with some of them. So I think that's what everybody that has a lot of data and CFD tools or numerical tools want to do, these surrogate models. That's definitely what everybody will try with machine learning.
Yeah, so with wave conditions, you need to have training data. And these kind of models, they're very useful in that sense. You get a lot of data, you can get all the different conditions, have a good foundation for training. Part of this NORA-SARA is a lot of process building also. We need to convert data, we need to think about different data sources. So in that sense, what we heard before lunch, thinking about process automation, this is also something where we are very much focusing on, to build those processes that not every step becomes manual. I think that's key.
Questions for him? Maybe you can you pass?
Hello, thank you for the presentation. I have a question more about the experimental side of things. So when you run a model of a coastal situation, then you compare it with a experimental small-scale setup, right?
Not always. So this is just very few data sets we have.
Okay. Yeah. But then you were to compare it with these small-scale experiments, you only compare it on a few given points of the model. And so have you experimented with image processing or video processing of a top view of the model, for example, to get the wave pattern on all of the harbor rather than just on some points?
There's some, I mean, that's not our work, the experimental work. So we are really focused on the model development and modeling. But yeah, I'm aware of that something.
Jousef, hi. Thank you for the presentation. I just have like a really easy question. What do you mean by quasi-static mooring model?
Dynamic mooring gives more accurate, much more. Fast boat.
Join us again at the Coffee Lounge, where will take place the Data Bytes social event, where the purpose is also, as shared by Luis Sarmiento yesterday, if you want to run your own simulations using Inductiva's API, you can do it, and our team will be there also to support you in generating the data sets. So thank you, we'll see you in a bit.